Welcome to the LearnCarts Speech Recognition Certification Training. Welcome to Module 1, Speech and its Types. After completing this lesson, you should be able to understand three things. Number 1, speech and speech processing. Number 2, digitization and recording of speech signals. And 3, acoustic phonetics and articulatory phonetics. Part 1, Introduction to Speech. So what is speech? Well, the most common means of communication is speech. It's defined as the expression of thoughts and feelings by articulating sounds. So why speech recognition? Well, if a model is built which takes inputs in the form of speech or vocal inputs and then processes the data, this would require the data to be converted into the form of text. This can be done using speech recognition. So what are some of the aspects of speech? Well, first, there's the perceptual variability of speech, which is present in the forms of various languages, dialects, and accents. Secondly, there's the intricate variability at the speech signal level, which is present in the form of varying amplitudes, durations, pitches, timbres, and speaker variability. How does speech differ from other forms of data? Well, speech differs from other forms of data due to two characteristics. Firstly, speech signals do not contain invariant units. An invariant is a property held by a class of mathematical objects which remain unchanged when transformations of a certain type are applied to the objects. So by saying that speech signals do not contain these invariants, what that means is that the properties of the speech signals could change when we apply transformations to them. Something to keep in mind. Secondly, speech can be both perceived and produced in a non-linear way. Just think about any conversation that you've had with someone where you do not tell of a sequence of events in the exact time sequence that they occur. This is definitely one of the largest challenges with speech. Additionally, text is written, or rather text is a written representation of a speech and is evolved to store and convey information over long distances. It is devoid of the previously mentioned intricate variabilities that exist in speech. Also, the intricate variabilities in speech make it more complicated to analyze, but provides additional information using the tone and amplitude variation. So here we can see how speech goes between a human and a computer. So for the human, we are inputting speech. And then the computer has to take that speech and synthesize it and create an understanding, which then generates a meaning. Out of that meaning, the computer then generates text again as a response and then outputs speech. Just think of any device that is driven by speech that you have used, maybe like a Google Home or an Alexa or Siri. That's how all of these things ultimately work. So, categories of speech sounds. Well, there's three. Firstly, we see voicing. Voicing is the vocal cords that will be vibrating. So literally as we're talking, our vocal cords are vibrating. Secondly, there's frication. And in this, there will be constriction and turbulence in the vocal tract. And then third, you have plosion. And in this, the air pressure builds and is released in a sudden noisy burst. Part 2, speech processing. So what is speech processing? Well, there's many aspects to speech processing. You have your input, manipulation, storage, transfer, and then finally output. But speech processing itself is defined as the study of speech signals and the methods of processing that speech, or rather those speech signals. And it refers to the intersection of digital signal processing and natural language processing. So it's a combination of those two things. Speech processing technologies are used for a variety of things, including automatic speech recognition, digital speech coding, and text-to-speech synthesis. All of these are present in spoken language dialogue systems. So here we can see how speech is actually processed. So on the far left, we have our raw or tagged text, which is then run through text analysis. There's three parts to that. First, there's document structure detection. Secondly, text normalization. And then finally, linguistic analysis. Once the text analysis is done, we then move to phonetic analysis, which includes homograph disambiguation and grapheme to phoneme conversion. And we'll be looking at these things in depth later on. After phonetic analysis, we have prodosic analysis, which looks for pitch and duration. And then finally, speech synthesis, which is the voice rendering. And the output of all of this is synthetic speech. There are many forms of speech processing, or rather, speech processing is used in a lot of different applications. First, we have speech emotion recognition and intelligent household robots. Yeah, speaker verification, speaker identification on the basis of mood, interactive voice response systems. You have train reservation systems, automation of operator services, voice dialing, voice navigation of a desktop on a computer, and then also call center information. And you may have interacted with one or more of these types of things. So for instance, voice dialing, a couple examples are if you have an iPhone where you can tell the phone itself to call one of the contacts that you have. Automation of operator services have been in use for a very long time. Just think of all of those phone trees with which you've had to interact when something says, please push or say 1, push or say 2, all of that kind of stuff. Speech production. Speech is produced via coordinated movement of articulators. The spectral characteristics of speech are influenced by the following: the source, the vocal tract shape, and radiation. When I say source, I mean what is producing the sound. For vocal tract shape, what I mean is this. The vocal tract acts as a resonator and a filter for all parts of the sound created by the vocal folds or the vocal cords. And radiation is how the sound moves from the source through whatever medium it encounters. For instance, air or a filter in front of a microphone. Speech articulation itself is characterized by manner and place. And what we mean by that is looking at things like vowels, semivowels, fricatives, nasals, and also stops. Now, there's a lot of value of spoken language. First off, it's economical, so it can be transmitted or received relatively inexpensively. It's natural, it requires no special training. After all of us since birth are trained to speak in whatever our native language is. So it just comes naturally to us humans. Next, it's flexible. It leaves our hands and eyes free. And then finally, it's efficient. It has a high data rate. A lot can be transmitted through speech. Now, there's two main types of speech recognition systems that you may have already had some interaction with. First, there's speaker identification speech recognition. So these are systems that are used for things that need a large vocabulary for cooperative speakers in benign environments. Or you might have systems that have moderate vocabularies for spontaneous speech over the phone. Secondly, we have the commercial recognition systems, so things that are used for dictation. For example, IBM and Microsoft have a number of different applications of this. Nuance, so an application called Dragon Naturally Speaking, are all commercial recognition systems. And then finally, everything that you might do via the telephone that you are interacting with via voice. Again, the phone trees that we were talking about earlier. And so you might see these in AT&T or VST, or again, the company Nuance has a lot of these systems as well. What makes speech recognition so hard? Well, first off, there's a lot of phonological variation. In other words, the way in which people pronounce something, even within a single dialect, can really vary. And that can definitely make it hard for computers to be able to recognize their speech, even though two people might be speaking the same language, the same dialect of that language. The way that they pronounce that language can cause computers difficulty. Something that for us is very easy to do, to recognize, is actually very hard for our computers. Secondly, you have a lot of individual difference, which almost kind of sounds the exact same as phonological variation. In other words, you and I might use completely different language to describe the same thing. In English, we have hundreds, thousands of words. Many words can mean the exact same thing, or depending on the text or the context rather, right, words can mean completely different things. Next, you have environmental factors. Things like if someone is speaking when in a crowded room, can the speech recognition system pick out only their voice from all of the background noise? Again, something that's not exactly as easy for a computer to do than we. Diversity of languages used is a big one. There are literally hundreds of languages spoken on Earth. So which languages does your speech recognition system need to support? And then how many dialects of each of those languages might you then want to support as well? And then you just have a lot of real world issues. So even though we all might speak English, the way in which we say those words could be very different. Accents, things of this nature. You may have heard stories of when the Amazon Alexa first came out, there were a lot of difficulties for people with accents where Alexa could not recognize what they were saying. Even though they were speaking English, their accents were such that Alexa itself had a lot of problems trying to figure out what it is they were saying. So there are a number of related areas of research around speech recognition. Firstly, spoken understanding or rather speech understanding and spoken dialogue is a very big one. Multimodal interaction. Currently, a lot of systems are one way. For instance, on Alexa, you can't really have a back and forth conversation with an Alexa. If you're trying to purchase something, then it will ask for a very simple response. Something like, do you want to purchase this product? That kind of thing. But for the most part, a lot of these systems do not have, so far, a lot of back and forth interaction to them. Thirdly is audio-visual analysis, as an example called AVSR. Fourth area of research is spoken document retrieval. So how do you basically retrieve things? You can think of like search could be an example of spoken document retrieval. Fifth is speaker identification and verification. How do you identify who that person is that is speaking and actually verify that that is the person that you think is speaking? In other words, is it me? Is it you? How do you know that? How do you get a computer to be able to identify the speaker and verify that that's that person? Again, something that's fairly easy for we as humans to do, but very difficult for computers. Six is paralinguistic analysis. In other words, emotion. How can you really tell emotion from the way that someone is saying something? This is especially a big challenge across cultures, where some cultures might see, for instance, sadness very differently than in America or India or China. So because of our culture and just the meanings that we have for a lot of stuff that we use language for, that in of itself can present a lot of challenges to computers. So that's a whole area of research in of itself. And then finally, acoustic scene analysis. Welcome to the Audiophile Analysis Speech Processing Basics demo. In this demo, we will understand how to analyze an audio or speech signal with Python. To do so, we'll be using some Python libraries. Python has some great libraries for audio processing, including Librosa and PyAudio. There are also a few built-in modules for basic audio functionalities. Let's get started. To start, go to the Start menu of your window and open the Jupyter Notebook. Once the Jupyter Notebook is initialized, you'll see a link that redirects you to the browser. Once there, click on New, and then Python 3 to create a new Jupyter Notebook using Python 3. Now, let's rename this file as Analysis of Audio Files. Now let's see how to implement this project. First, we need to import the required packages, including Librosa, using the import command. Librosa is a Python module which is used to analyze audio signals. In general, you can load any audio file using this and work on it. After importing Librosa, specify the audio path that needs to be imported. To load the file, let's use the load function. This is x,sr equals librosa.load and then the audio path, which is the full path to the audio file. This will load the audio file mentioned in that path that you just put in. Please ensure that the complete path of the audio is specified. If not, show the steps shown on the screen. Now click the Run button to run the code. Now, let's play this audio file directly in Jupyter Notebook using the ipython.display.audio method. To use this method, we need to import ipython.display as IPD and then pass the audio path as a parameter to the ipd.audio function. Run the code, and you can now play the audio directly from within Jupyter Notebook. To check, play the audio once. Now, let's visualize this audio file. We can plot the audio array using librosa.display.waveplot. First, let's import matplotlib, saying import matplotlib.pyplot as PLT, and import the Librosa display package using import librosa.display. Now let's specify the figure size. This is the size of the output plot. And then plot the wave plot by using, or rather passing, the audio as a parameter. Now run the code and you can see the output. Let's try to display the spectrogram. To do this, let's use the stft function, which converts data into a short-term Fourier transform. It's used to convert signals such that we can determine the amplitude of a given frequency at a given time. We also use the specShow function to display the spectrogram. The code for this is as follows. X equals librosa.stft of x, xdb equals librosa.amplitude_2_dB, and there we pass in the ABS, or absolute value of capital X. Next, plt.figure, passing in fig size equals 14,5. That's the size of the plot that you'll see. And then librosa.display.specShow, passing that the parameters xdb, sr equals sr, x_axis equals 39, time equals 39, y_axis equals 39, and finally hz equals 39. Hz is hertz. And then finally, enter plt.colorbar. Now run the code and you'll see the output in the form of a color bar. The vertical axis here shows the frequencies from 0 to 10 kilohertz, and the horizontal axis shows the time of the clip. Since we see that all this action is taking place at the bottom of the spectrum, we can convert the frequency axis to a logarithmic one. So let's now interchange the axis using the code below. librosa.display.specShow, passing in the parameters xdb, sr equals sr, x underscore axis equals time, and this time y underscore axis equals log. Now we print that out using plt.colorbar. Now run this code and you'll see the output with the interchanged axis. Now let's write this output to a file. To do so, we use the librosa.output.write_wav function. It saves a NumPy array to a WAV file, and you can write this output of any audio file to another audio file as and when required. Let's specify the path of the file to which we need to write the audio. Now run the code, and you can see that a new file has been created as example.wav with all the data written into it. Here, we have successfully completed the analysis of an audio file. Part 3, digitizing and recording of speech signals. How do we record this? How does this happen? Well, digitizing and recording of speech signals can be referred to as the conversion of speech from telephonic transmitter, a telephonic transmitter, from its analog waveform to a binary format. So in other words, we are speaking, and when we speak, it's in an analog format, and computers do not speak analog, they speak binary. So we are basically taking those speech signals, or our speech, and transforming them from analog to a binary format. And this goes through 3 main steps, or the digitization methods can be divided into 3 steps really. Firstly, we have the waveform coder, which takes the actual waveform and produces a series of ones and zeros as its representation. Secondly, we have a hybrid coder, which uses both waveform and parametric principles in its production. And then third, there's a parametric coder, which attempts to detect certain characteristics of the speech, such as pitch and amplitude that we've referred to before. So that's really the basic method. Welcome to the digitization and recording of speech demo. In this demo, we will understand how to digitize and record speech. Have you ever wondered how to add speech recognition to your Python project? If so, then keep reading. It's easier than you might think. Here, we are going to show you how you can extract the information from your audio files. As a first step, download the required packages using the command line, using either pip or conda. Here, we're going to use pip to install our speech recognition Python module. To do so, open the command prompt and type the command pip install speech recognition, and then press enter. Once the packages are installed, go to the Start menu of your window and open the Jupyter Notebook. Once initialized, you'll see the link redirect you to the browser. Now, click on New, and then Python 3 to create a new Python project. Let's rename the file as digitization and recording of speech. Now, let's import all the required packages using import speech underscore recognition as SR. We must now verify the installation by opening an interpreter session and typing sr dot underscore underscore version underscore underscore. Run this command and you'll see the output as 3.8.1, or perhaps a newer version if one has come out since recording this demo. All of the magic in speech recognition happens within the recognizer class. So let's create a recognizer instance. To do so, in your current interpreter session, just type r equals sr dot recognizer and run that command. Let's now use the record function to capture data from a file. Type the following command into your interpreter session to process the contents of the harvard.wav file, which is located in one of your system directories. Harvard equals sr.audio file, harvard.wav. Let's check if the file name is correctly entered or not. Please ensure to enter the complete path to the audio file. Now keep in mind that the location must be a file location from your local disk as shown on the screen. Otherwise, the code isn't going to work. Now, let's use the record function to capture data from the file using the commands below. With Harvard as source, audio equals r.record, passing in source to that method. The context manager opens the file and reads its contents, storing the data in an audio file instance called source. Then, the record method records the data from the entire file into an audio data instance. You can confirm this by typing type and then passing in that audio variable that you just created. Run the command and you'll see the output as speech underscore recognition dot audio data. This confirms that the recorded data is in fact stored in the audio data instance. Now, let's understand how to recognize the speech in the audio file. To do so, let's invoke the recognize underscore Google function to help us recognize any speech in the audio. Depending on your internet connection speed, you might have to wait several seconds before seeing the result. Enter and run the command below, r.recognize underscore Google, and then passing in that audio parameter, or rather the audio object that you created earlier. You can now see the output, which recognizes the speech in the audio file attached, as shown on the screen. Let's now understand how to capture segments with offsets of the audio. What if you only want to capture a portion of the speech in a file? The record method accepts a duration keyword argument that stops the recording after a specified number of seconds. This can be done using the commands below. With Harvard as source, audio equals r.record, passing in source, comma, duration equals 4. So this sets the duration to 4 seconds. You can see we have kept the value of duration as 4. So let's use the recognize Google function again and see if it captures the speech only for the specified duration. Run the command, and you can see it prints only the first line, the salesman old beer drinkers, which comes under the duration specified. You can also change the duration and check the output again, something I'll leave to you. Here, we have successfully performed the digitization and recording of speech. Part 4, Acoustic Phonetics and Articulatory Phonetics. So what are acoustic phonetics? Well, it refers to the research of physical properties of speech and is used to analyze the sound waves with respect to their frequencies, amplitudes, and durations. So a waveform is one of the ways to analyze the acoustic properties of speech. And it's used to plot the pressure changes, which highlights the air particles being compressed and rarefied. So you can think of it like a tuning fork. So a tuning fork can actually be used to understand air fluctuations and oscillations when the sounds are perceived. So here we have an example of a waveform. And this is the waveform of a vowel. And so this is what we mean by the waveform. So 3 parts to articulatory phonetics. First off is the initiation, which is the process of setting up of air in motion through the vocal tract. Phonation is the process of modifying the airflow when it passes through the larynx. And then third, articulation, which is the process of shaping the airflow to generate particular sound types. So there's 3 aspects of phonetics that we'll take a quick look at. And what we mean is the phenomenon which examines the creation of sounds of speech with the organs of the vocal tract. In other words, how do we as humans actually produce speech? So articulated phonetics can be broken down into the following 3 areas. We have voice, place, and manner. So there's some phonological variation. And what we mean here is the acoustic realization of a phoneme, and that depends on the context in which it occurs. So here we have 3 different variations of this we can see. First off, we see if you say tree, or T rather. Secondly, when you say tree, and then steep, and city, and beaten. So these are the waveforms, and you can see the different waveforms that are produced when each of these words is spoken. Welcome to the Human Speech Production demo. In this demo, we'll understand how to produce human speech using APIs. There are several APIs available that we can use to convert text to speech with Python. One such API is the Google Text-to-Speech API, commonly known as GTTS API. GTTS is a very easy-to-use tool which converts the text entered into audio, which can be saved as an MP3 file. To do so, open the command prompt and let's download the required packages from the command line using either pip or conda. Here, we're going to use pip to install our GTTS Python module. Type the command below and click enter. Pip install GTTS. Next, go to the Start menu of your window and open the Jupyter Notebook as shown. Once the Jupyter Notebook is initialized, you'll see the link redirecting to the browser. Next, click on New and then Python 3 to create a new Python project. Let's rename the project as Human Speech Production. Now, let's understand how to implement this project. The first step is importing the required module for text-to-speech conversion. Do that as follows. Import GTTS, and then from GTTS, and import OS. Run the code now in order to import these libraries. Next, let's define the text for which we want to produce human speech. Let's say, welcome to your first test of human speech production. Once this is defined, run the code. Now, there are various human languages available, so we will also have to define the language in which we want to produce the speech. Let's define the language, say English this time. Let's now convert the text to human speech using the GTTS API, using the following code. My obj, or object, equals GTTS. And we'll pass into this method different parameters. Text equals my text. Lang equals language. Slow equals false. We can see that the text in the language in which we want to convert the text are passed as parameters to the GTTS function. We have also marked slow equals false, which tells the module that the converted audio should have a high speed. Run the code. Oops, we have an error that says my text is not defined. Let's run all the cells again, and this should solve the error. Once the text is converted into speech, we would have to convert it to an audio file. Let's save the converted audio into an MP3 file named welcome. To do so, we will use the save function and pass the audio name as a parameter, as shown on the screen. Please make sure to specify the complete path where the file has to be saved. Now run the file. Oops, we have an error again. Let's change the path or check if the path is correct and run the code again. Yes, this helps. Let's now try playing the converted file using os.system command as shown on the screen. Now run the code. And here we have successfully completed the process of producing human speech using the GTTS API. So key takeaways for this. So now you have an understanding of speech and speech processing, digitization and recording of speech signals, how that happens, and then also acoustic phonetics and articulatory phonetics. Thank you very much. Module 2, Automated Speech Recognition. After completing this lesson, you should be able to understand what an audio signal is, parameters of an audio signal, how frequency affects a wave, different types of signals, signal sampling, feature extraction techniques for an audio signal, template matching, acoustic modeling and language modeling, And finally, hidden Markov models. Part 1, Introduction to Audio Signals. So we want to start out by just asking the question, what is an audio signal? An audio signal is a longitudinal vibration that gets underway by any occasion that produces vitality. For example, a vibrating object. And audio signal is composed of sound waves. And sound waves are the vibrational signal that are produced by moving energy through a medium as it propagates away from the sound source. And there are sound waves everywhere. I'm creating sound waves right now with my voice. When objects drop, they also produce sound waves. Literally anything that produces a sound, that sound is sound waves. And here's what that looks like in chart format. So here we have an example of an acoustic longitudinal wave that was created via sound pressure. Now, audio signals have many different parameters. We have the amplitude, we have crest and trough, the wavelength, cycle, and also frequency. This chart explains all of those things. So starting from the left and moving to the right, first off at the top, we see that this wave is actually traveling from the left to the right. And this in of itself is also a transverse wave. Now, the red line that you see in the middle is what's called the undisturbed position, meaning if there was zero audio at that time, that's where the wave would be, is right there at effectively what you can think of as the zero. Now, the amplitude of the vibration is the distance between that undisturbed position and what's called the crest, which is the top of the wave. And the vibration is the total distance between the top of the wave and the bottom of the wave. And again, the top of the wave is called a crest and the bottom is called the trough. Now, when we say a wavelength, what we're talking about is the distance between the crest of one wave and the crest of another, or rather in between the crest of a wave. So how does frequency affect a wave? Well, we can see that here in this chart. Now, on the left-hand side, we have a wave with a long wavelength. And on the on the right-hand side, we have a wave with a short wavelength. So on the left, the long wavelength wave is a high velocity wave, whereas on the right-hand side, we have a low wave velocity. And you can see then how that's impacted by the length of the wavelength itself. Part 2, different types of signals. So what is a digital signal? A digital signal refers to a converted electrical signal into a pattern of bits. And this has a discrete value at each sampling point, unlike an analog signal, which is a continuous signal comprising time-varying quantities. And we can see that here in the diagram on the bottom half of this slide, where all parts of this signal are either a 0 or 1. And this is very different than an analog signal. So what is the difference? Well, an analog signal is a continuous signal of different amounts of time. And unlike a digital signal, there are regular changes in an analog signal at each sampling point. And here, while this particular diagram shows that we have a definite peak and trough at certain times, that just so happens to be what this diagram shows. However, the point though is that the analog signal, there's more than just a 0 or 1. We see we have a range of values as we travel up and down this particular wave. So that's the big difference between digital and analog signals. Digital is zeros and ones, and analog is really a continuous range of values over time. Part 3, signal sampling. Well, sampling is a technique that's used to transform a signal from continuous to discrete time. In other words, from analog to digital. And signal sampling itself is the process of converting a continuous time signal to a discrete signal so that computers can digitally process the data. Computers by themselves do not handle analog data. We have to convert that into a digital format in order for the computers to be able to work with it. And we can see how this might happen on the top right, where we start off with our message, which as you can see is an analog wave. We then sample that signal, effectively turning it into zeros and ones, and then we have our outputted sampled message. So what about sampling rate though? What does that mean, and how fast should we actually sample a signal? Well, a continuous time signal can be shown in its samples and retrieved if the sampling frequency fs is greater than or equal to twice the highest frequency element of the message signal. In short, in a very short equation, fs is greater than 2fm. And that is the equation for sampling rate. So, feature extraction. What is that? Well, feature extraction is a process that explains most of the data, but in an understandable way. And this technique is important for algorithms of classification, prediction, and recommendation. Feature extraction is used in all of these. And again, we're trying to convert the data into an understandable format. And so here in the chart, we see we have amplitude, frequency, and time. And so these are just some of the features that we can extract from audio signals. Additionally, some features of a signal include the zero crossing rate, the spectral centroid, spectral roll-off, and something called the MFCC, or mel-frequency septal coefficients. Zero crossing rate. The zero crossing frequency is the signal shift along a line. In other words, is the speed at which the signal changes from positive to negative or backwards. So you can think of it kind of like a velocity. And so that's what we mean by speed. And this is used in both speech recognition and retrieval of music information. So if you ever use Spotify or any of these music services, they are using zero crossing rate. Spectral centroid. Spectral centroid is used to indicate where the center of mass for a sound is located and is calculated as the weighted mean of the frequencies present in the sound. Now, spectral roll-off is the frequency below which a given amount, say 85% in this instance, of total spectral energy lies. MFCC, mel-frequency septal coefficients. So aside from being a large word, it's difficult to say what exactly does this mean. Well, it's actually one of the most effective ways for removing an audio signal element and is used mostly when operating with audio signals. And specifically, a signal's MFCCs are a small set of features, usually numbering around 10 or 20, that define a spectral envelope's overall shape in a concise manner. Spectrogram. A spectrogram is a visual representation of the audio or other signal frequency range as it varies over time. It's a reflection of shifting frequencies of given music signals in terms of time. And what this can be used for is to determine the amplitude at a given time of an audio signal of different frequencies playing. And here on the bottom right, we can see a visualization of a spectrogram. And you'll be doing this later on, producing one of these yourself. Template matching. Templates are usually built for whole words. Template matching is the method of matching unknown speech to a collection of pre-recorded words or models. You can think of this almost like a fill-in-the-blank kind of thing. And this method has the advantage of using precisely detailed word models, but it has a downside of correcting pre-recorded templates. In other words, you're using pre-recorded, because you're using pre-recorded things, it's not completely on the fly. And so you have to match potentially n number of templates when using this technique. But it does have a lot of upsides, which is where you get precisely detailed word models or precise outputs, because you're effectively just filling in the blanks with the rest. Welcome to the sampling theorem demo. In this demo, we will understand the sampling theorem. Let us first see what the sampling theorem states. Well, the sampling theorem states that a continuous signal, x of t, band limited to b hertz, can be recovered from its samples x of n equals x times n times t, where n is an integer if t is greater than or equal to 1 divided by 2 times b, without loss of any information. And we call 2b the Nyquist rate. Let's see how it affects with the help of some code. To do so, let's import the packages or dependencies required for this demo. Import linspace, comma, cos, comma, pi, comma, ceil, comma, floor, and a range from NumPy. Import plot, show, and axis from PyLab. Let's now see how to write code for sampling a signal limited to 30 Hz with a limited sampling rate of 600 Hz. To do so, let's define a few parameters. F is the frequency in Hertz. T min and T max are the minimum and maximum time range. T equals linspace times T min, comma, T max, comma, 300 is used to create a sequence of numbers from T min to T max. The linspace function is similar to NumPy, with the difference in that it creates evenly spaced numbers. X equals cosine of 2 times pi times t plus cosine of 2 times pi times f times t is used for signal sampling. The plot function will plot the graph of the signal. You can even run these separately to see the output separately. However, let's run it all to complete the entire sampling process at once and examine the final output. Let's now see how to perform sampling with a sampling rate of 60 Hz. Here, we'll be using the Nyquist rate. How is sampling affected by the Nyquist rate? Well, sampling at a rate below the Nyquist rate is called undersampling, which leads to something called the aliasing effect. To do so, let's define the parameters as shown. T is the time, n min and n max are the minimum and maximum Nyquist rates. The range function returns an ND array object containing evenly spaced values within the given range, that is, within the given range of Nyquist values that we've provided. X1 calculates the signal sampling, and we use the plot function to plot the graph. Now, let's plot a signal using a frequency, which is below the Nyquist rate. So, let's perform signal sampling with a sampling rate of 25 Hz. Please note that 25 Hz is under the Nyquist rate. To do so, let's again define the parameters. Again, t is time. Nmin and Nmax are the minimum and maximum Nyquist rates. The range function returns an ND array object containing evenly spaced values within the given range. Again, that's the given range of Nyquist values that we provided before. X1 calculates the signal sampling, and the plot function plots the graph. Let's now define the axis values and use the show function to display the final output of all the signal sampling done so far. Once the code is complete, run the code and you'll see the output. The blue lines are the output of the first part of the code. That is, the sampling of a signal limited to 30 Hz with a sampling rate of 600 Hz. The blue dots represent the output of the second part of the code using the Nyquist rate. That is, the sampling of the signal with a sampling rate of 60 Hz. The red part represents the last part of the sampling, which is the frequency below the Nyquist rate. That is, the sample of the signal with a sampling rate of 25 Hz. To be more specific, the blue curve is the original signal. The blue dots are the samples obtained with the Nyquist rate, and the red dots are the samples obtained with 35 Hz. It's easy to see that the blue samples are enough to cover the blue curve, while the red ones are not enough to capture the oscillations of the signal. Part 4, Acoustic Modeling. Acoustic modeling. An acoustic model is a classifier that tries to identify the pronunciation being spoken based on an input acoustic feature. And here we see an example of that. On the left side, we have our signal, which then gets fed through a feature extractor. The features that are extracted are then run through an acoustic model, which gives us our output that you see on the right-hand side. Now, 3 points to consider about acoustic modeling. First off, the relationship between acoustic knowledge and phonetics is developed in acoustic modeling. And acoustic models play a major role in system performance and is also responsible for the computational load, meaning how much processing is required to actually develop and then use those models. And the hidden Markov model, or HMM, something that you'll see also even more in this module, is commonly used an accepted model. Is the most commonly used and accepted model, and is an effective training and recognition algorithm. But we don't just have HMMs. In fact, for acoustic modeling, we have multiples. And again, acoustic modeling refers to the process of statistical representations for the computed feature vector sequences from the speech waveform. And there are, again, multiple variations of models that you can try out. We have the hidden Markov model, or HMM, a segmental model, supersegmental model, neural networks, a maximum entropy model, and also conditional random fields. Deep learning in acoustic model. Here we have a graph showing how to use a neural network, or NN, to predict the probability of each Gaussian model mixture, or GMM. Much like ones we've seen previously, we have our signal on the left-hand side. That signal is then run through a feature extractor, which creates a vector of features, which is then fed into our deep neural network, which ultimately gives us the output that we see on the right-hand side. NN training as an acoustic model. With force alignment, we can use a deep neural network with supervised learning to process an audio signal. On this graphic, we start at the top with our audio signal. We then, on the left-hand side, as the input to our deep neural network, have our MFCC feature vector, which you can see an example of in the gray boxes. That gets then input into our deep neural network that then produces a vector. And that vector is essentially the answer from our force alignments. And with force alignment, again, you can start DNN supervised learning, but other features can also be appended to the input as well. For example, here we see we're adding speakers or I vectors in as well, and we can also add context frame and additional information into basically our set of features as well. Part 5, language modeling. A language model includes the conceptual weaknesses in the language available to produce event probabilities. After a word sequence, it induces the probability of a word occurrence. So what we're trying to really predict is the probability that a word is going to occur. So with language modeling, there's 3 parts to consider. First off, it identifies words and phrases with different tones, which is an important thing. Ambiguities are easier to resolve if the data from the language model is combined with a pronunciation model and an acoustic model. So combining models is a technique called ensembling and is very popular because you can leverage the power of multiple models instead of having just one. And so that's what this is referring to, is you can actually resolve these ambiguities better if you combine language, pronunciation, and acoustic models together. And then finally, it helps the speech recognizer consider the probability of a word string regardless of the acoustics. And there's 2 types of language models. There's the statistical language models, and then there's natural language models. Now, a concept in this is using n-grams, or an n-gram model. So an n-gram language model predicts the probability of a given n-gram with any sequence of words in the language. And this is important because if we have a good n-gram model, we can predict basically the probability of seeing a given word, given the history of previous words, where the history contains n to the minus 1 words. So in other words, here on the right-hand side, we have the phrase, "Can you please come?" And then here is filled in. And here is the word that we want to predict based on the history, which in this case is, "Can you please come?" So you've probably seen this used in many instances, especially with autofill in Gmail or any search engine, you'll see this commonly. Any type where you have effectively an application that is trying to predict the word that you will use next is using this kind of model. So how do n-gram language models work? Well, the probability is computed in two steps. First, you want to apply the chain rule of probability. And then secondly, you apply a very strong simplification assumption to allow us to compute P of W1 to Ws in an easy manner. And the chain rule of probability is there below. Part 6, building a basic language model. So now you're going to see how to build a basic language model using Python. And to do so, we're going to use one of the most popular natural language processing or NLP libraries out there for Python called NLTK, which stands for Natural Language Toolkit. This is an open source Python package that is pretty much the de facto standard, or one of them at least, for doing natural language processing in Python. And it has a lot of very powerful features. And looking over the code on the right-hand side here, we can see the first import statement says nltk.corpus import Reuters. And what a corpus is a collection of documents. And for natural language, having these collections of documents is important because that's what we use to actually train our models. And then the second line of code there, where it says from NLTK import bigrams and trigrams, these are the basic building blocks of natural language processing that we're going to be using. And you're going to see even more of those later on. So here again, we want to build a basic language model using trigrams of the Reuters corpus. Now, the Reuters corpus itself is a collection of 10,788 news documents totaling 1.3 million words. So definitely a lot of words. And a language model can be built with only a few lines of code, again, using this NLTK package. And as you can see here, a chunk of this code is just importing the libraries that we want to use. But actually creating the model is very simple. And what we're going to do is after we import all the libraries, we'll create a placeholder for our model. And then we're going to count the frequency of co-occurrence. In other words, words occurring in sentences together. And then we're going to transform those counts into probabilities. And now here is a script that's going to generate a random piece of text using the n-gram model that we just created. We start out by importing the random library, which is built into Python. We have our starting words. We define an additional parameter of sentence finished. And until we get to the end of the sentence, what we're going to do is we're going to just keep looping through and creating probabilities for those. And then ultimately, we're going to print everything out. And now here is the output of that model. So we can see that the first line says, today the company's stock rose after a brokerage house hurt the economic area. A delegate to Cocoa and the dealer's hat blah, right? Like a lot of this stuff is basically unreadable, right? But that is effectively what the algorithm is trying to do is guess, given the first part of the sentence, which we defined earlier as today it then tries to fill in the rest of the sentence with the information from the corpus which we trained the model on. Now, even though this doesn't make sense and it wasn't very sophisticated of a model, this is the same underlying principle which is used by Google, Alexa, and Apple for language modeling. So all of the building blocks are the same. Now, there are limitations of the n-gram approach to language modeling. First off, the higher the n, the better the model is. So to really get this right, you have to have a really high n, which can require a lot of compute resources. Secondly, there are sparse representations of language, or rather they are a sparse representation of language, meaning they don't really necessarily represent language very well. Just a little piece of a sentence doesn't necessarily represent the entire sentence, depending on how many words you actually put together from the sentence itself. And also, it's going to give you zero probability to all words that are not present in the training corpus. And what that means is that you really, to do this effectively, need a very large training corpus. As an example, some people have gotten all of Wikipedia, they've downloaded that and trained their language models on Wikipedia. And as you can imagine, search engines like Google or DuckDuckGo or Yahoo have huge amounts of data already because they have been indexing everything from the internet. So they have huge training corpuses. And again, if you want to take this approach, you really need to have a very large training corpus to ensure that you get as many words, or you can create effectively as many n-grams as possible. Welcome to the audio signal feature extraction demo. In this demo, we will learn how to extract features of music files that will help us to classify music files in different genres, or to recommend music based on your favorites. Let's use Librosa for extracting and analyzing the features from the audio signal. To do so, let's first install the Librosa package using command conda install -c conda-forge Librosa. This will load all the packages required. Let's also restart the kernel. Now, let's install Numba using the following. Conda install -c numba space numba. Restart the kernel again. Now to load the audio, we will need to install ffmpeg using the following command. Conda install -c mempo space ffmpeg. Once all the packages are installed, let's import the packages or dependencies required to perform this task. Import Librosa. Import pyplot as plt from matplotlib. Import librosa.display. Now, specify the audio path. Before doing this, you'll need to upload the audio file into a folder, say audio. Now specify the audio path to a variable, say audio_path equals path to the audio file. Once you've declared the path to the file, now load the file using the following. x, sr equals librosa.load. Open paren, audio path, sr equals none, close paren. And then print that using the following command. Print open paren, type of x, type sr, close paren, close paren. .load loads an audio file and decodes it into a one-dimensional array, which is a time series x. and SR is the sampling rate of X. The default SRIS is 22 kHz. Now, once the file is loaded, let's try and display the spectrogram. To do so, let's use the STFT function, which converts data into short-term Fourier transform. It's used to convert signals such that we can determine the amplitude of a given frequency at a given time. We can also use the spec_show function to display the spectrogram. The code for this would be x equals librosa.stft open parens x close parens. xdb equals librosa.amplitude underscore 2 underscore dB open paren the absolute of x close paren and next plt dot figure open paren fig size equals 14,5. librosa.display .spec_show open paren xdb, comma, sr equals sr, comma, x-axis equals time, comma, y-axis equals hz. And then show it using plt.colorbar. And you can see the output in the form of a color bar. After doing this, let's understand the use of zero crossing rate in feature extraction. It's the rate at which the signal changes from positive to negative or back. It's used in extracting features and other information from audio files. To do so, we again load the audio file and plot the signals using the waveplot function as shown in the code. We define the figure size of the figure. Run the code and you will see the output as shown. Now, once we get the output of zero crossing, we will print the spectrum only for 100 array columns. To do so, we define two values at a difference of 100. Say, n0 equals 9,000, n1 equals 9,100. We then specify the figure size and plot the graph. The grid function is used to display the output in grid view. Run the code, and you can now see the output in grid form, and the output is shown only for 100 columns as specified. As we can see, there's 3 zero crossings in the given graph. We can also calculate zero crossings using the given code. 0 underscore crossings equals librosa.0 underscore crossings X N0 to N1, comma, pad equals false. And print that using the print function and passing in sum of 0 underscore crossings. Run the code and you will see the output. Let's now understand the working of spectral centroid. It indicates the location of the center of mass and is calculated as the weighted mean of the frequencies present in the sound. If the frequencies in the music are the same throughout, then spectral centroid would be around a center. And if there are high frequencies at the end of the sound, then the centroid would be towards its end. Let's write the code to do this. Import sklearn, spectral underscore centroids equals librosa.feature.spectralcentroid x, comma, sr equals sr, close paren, open bracket, 0, close bracket. And then to see the shape, type spectral underscore centroids dot shape. The spectral centroid function is used to calculate the spectral centroid for each frame. Now let's compute the time variable for visualization using the following code. Frames equals range, open paren, len, open paren, spectral underscore centroids, close paren, t equals librosa.frames underscore to underscore time open paren, frames, close paren. Now let's normalize the spectral centroid for visualization using the following method. Def normalize, open paren, x, comma, axis equals 0, close paren, colon, return sklearn dot preprocessing dot minmax underscore scale open paren, x, comma, axis equals axis, close paren. This will return the normalized value of the spectral centroid. Once this is done, we now have to plot the spectral centroid along with the waveform using the following code. librosa.display.waveplot, open paren, x, comma, sr equals sr, comma, alpha equals 0.4, close paren. plt.plot, open paren, t, comma, normalize, open paren, spectral centroids, close paren, comma, color equals R. Run the code, and you can now see that the waveform has been plotted. And there is a spurious rise in spectral centroid at the beginning of the signal, as high-frequency components have a chance to dominate, because the silence at the beginning has such small amplitude. Now, let's understand what spectral roll-off is and how it works. Spectral roll-off is the frequency below which a specified percentage of the total spectral energy lies, say for example 70%. To understand the working, we use the spectral underscore roll-off function. It's used to calculate roll-off for a given frame. After calculating the roll-off, we need to display the wave plot as shown in the code. Spectral underscore roll-off equals librosa dot feature dot spectral underscore rolloff, open paren, x comma sr equals sr, close paren, open bracket, 0, close bracket. Librosa.display.waveplot, open paren, x comma sr equals sr, comma alpha equals 0.4, close paren. plt.plot, open paren, t comma normalize, open paren, spectral underscore rolloff, close paren, comma, color equals R, close paren. Run the code and you will see the plotted waveform. Lastly, let us now also understand the working of MFCC. That is the melt frequency cepstral coefficients. It's one of the most important features used to extract information from audio. In order to calculate MFCCs of a signal, we will use the MFCC function and display the MFCC using the spec_show function as shown in the following code. MFCCS equals librosa.feature.mfcc, open paren, x comma sr equals sr, close paren, and then print, open paren, mfccs.shape, close paren. To display the MFCCs, use the following. librosa.display .spec_show, open paren, mfccs, comma, sr equals sr, comma, x underscore axis equals time, close paren. Run the code and you'll see the output. The first value represents the number of MFCCs calculated, and the other represents the number of frames available. We have now successfully extracted the features from the audio file. Part 7. Building a natural language model. So building a neural language model, while it might seem pretty daunting, is actually relatively straightforward. Now we can use a few of the libraries that are third-party libraries that have been created for Python, specifically NumPy, Pandas, and Keras. And now Keras effectively provides an API that's sitting on top of TensorFlow. So to run these, you'll want to download TensorFlow and then install Keras after that. But here on this slide, we can see all of the different libraries that we need to import. So NumPy and Pandas are imported in the standard fashion. And then from various parts of Keras, like the utils, preprocessing.sequence, models, layers, and callbacks, we're going to import everything that we need to develop a neural network architecture. Now here on this slide, we see how we're going to be pre-processing the text data. So we do things that are commonly used for all natural language processing techniques. So we can see that we are lowering the text, in other words, making everything lowercase. We're removing certain things. We're removing punctuation. That's not going to help us in any way, shape, or form. We're going to remove very short words. So if anything is basically greater than or equal to a length of 3, we're going to keep those words. So we still might have words like the, but we won't have and, in, words of that nature. We'll definitely not get into our list of words. And then finally, we pre-process the text using this method. Now, encoding sequences is another step that we do. And once we generate those sequences with the last method, the next step is to encode each character. And what this is going to do is actually give us a sequence of numbers. The key thing to remember here, and you may already know this, but I will just state it just in case, is that computers do not understand letters. They don't understand natural language. What they do understand is numbers. And so what encoding allows us to do is turn each of those characters into a sequence of numbers, and that is something that the computer can work with. So here we have some code for doing that. So first we're going to create a character mapping index, and then we define our encoding sequence method, which is going to take in a sequence and then effectively turn it into a list of numbers. And you can see how to use this method at the very bottom. And here is what that looks like. We have an array of arrays. So each of the characters in each of our sequences has been turned into a number, and then each of those has been appended to our list. And that's what we have here, an array of arrays, all numbers, characters converted into numbers. Now next we're actually going to build a model. And what we're going to do here is use the embedding layer of Keras to learn a 50-dimensional embedding for each of the characters. And this helps the model in understanding the complex relationships between the characters themselves. And we also have used a GRU layer as the base model, which has 150 timestamps. And then finally, a dense layer is used with a softmax activation to actually do the prediction. And here's the code on the right-hand side. As you can see, there isn't really a large amount of code necessary to actually produce a model. In fact, within 5 lines of code, we can define a sequential model. We give it our embeddings, and then we add our dense layer to it with an activation of softmax. And then finally, we're going to print out the model summary. And then to compile it, we just call model.compile, telling it what the loss function is, the metrics, and which optimizer to use. And then finally, we're going to fit the model. And what fitting a model does is it actually trains the model. And here in this method, we're passing it a training and test set. We're telling it to run for 100 epochs and at a verbosity level of 2, which determines how much information it's going to spit out as it's actually running each of those epochs. And then we're telling it what the validation data set is as well. And that's it. 1 line of code will train your model. Pretty awesome. Now, using that model, actually running it through or running something through to get a prediction is called inference. And once the model has finished training, we can actually generate text from this model given an input sequence. And the code to do that is on the right-hand side in this generate sequence method, which takes a model, takes our mapping, the sequence length, some seed text, and the number of characters that we want to look at. And so the first thing it does is it generates a fixed number of characters, basically using a loop. We're going to encode the characters as integers, truncate the sequences to a fixed length. We're going to run our prediction, calling the model.predict classes, and then create a reverse map integer to character. In other words, turning those numbers back into characters and then appending that to the text. And then we're going to return that text. So that's it. Within maybe 20, 30 lines of code, you have now built a neural network, you've trained it, and then you have actually created or run a prediction using that model. Welcome to the Force Alignment Expectations demo. In this demo, we'll understand the working of expectation maximization. So what exactly is expectation maximization? It's a powerful technique for creating maximum likelihood estimators when the variables are difficult to separate. So here, we will be experimenting in measuring from unseen groups. Suppose we have a population with 2 distinct groups of individuals with different heights. If we randomly pick an individual from the population, assuming we don't know which group the individual is from. So we measure that individual's height and choose another individual. The goal is to estimate the mean heights of the 2 distinct groups when we have an unlabeled distribution of heights sampled from both groups. Let's now simulate an experiment using code. We first need to set up the experiment of randomly grouping and then picking an individual from that group. Let's import all the packages or dependencies required for this task. Import division from __future __. Import array, linspace, random from NumPy. Import Bernoulli, norm from scipy.stats. Import cm from matplotlib. Import figure, subplots from matplotlib.pylab. Once all the dependencies are imported, let's set a random seed for reproducibility. Estimate MUA_true from the data. Estimate MUB_true from the data. Perform a distribution for group A using FA equals norm, open parens, MUA_true, 1, close paren. Perform a distribution for group B using FB equals norm, open paren, MUB_true, 1, close paren. To distribute each group equally likely, use the code FZ equals Bernoulli, open paren, 0.25, close paren. Now let's declare a function to simulate picking from each group n number of times. Let's declare a function, say sample, and pass n equals 10. Choose n of the coins, A or B, using tmp equals fz.rvs, open paren, n, close paren. Now, flip the chosen number n times. To do so, use the code return tmp multiplied by fb.rvs of n plus 1 minus tmp times fa.rvs of n. Once the data is flipped, let's generate some samples using the code xs equals sample of 1000. Now, let's plot the histogram of the samples and examine the density of each group. To do so, we use the hist function, which we'll use to plot a histogram based on the samples generated. To do so, we write the code as shown. F, AX equals subplots. X equals linspace, open paren. MUA_true minus 2 MUB_true plus 2 100 close paren. AX.plot open paren, x, comma, fa.pdf of x, comma, label equals group A. ax.plot x, comma, fb.pdf of x, comma, label equals group B. ax.hist, open paren, xs, comma, bins equals 50, comma, normed equals 1, comma, label equals samples. ax.legend, open paren, LOC equals 0. Run the code, and you can see the histogram generated. After examining the plot, we can come to a conclusion that we'll have to reconcile the samples in the overlap region, since these could have come from either group. Let's now understand how to maximize the expectations. The main aim of this is to somehow pretend we know the unobservable z-value, and then proceed with the usual maximum likelihood estimation process. Here, we are trying to use a maximum likelihood estimate after computing the expectation over the missing variable. The code below does that for us. SymPy is used to set up the functions symbolically and convert them to NumPy functions that we can quickly evaluate. The code L equals stats.density of NA times X plus stats.density NB times X divided by 2 is used to calculate the incomplete likelihood function. This is useful to keep track of the incomplete log likelihood. Next, we need to compute the expectation step using the code below. Def easy with the parameters x, mu underscore a, mu underscore b. Return norm mu underscore a dot pdf of x divided by norm of mu underscore a dot pdf of x plus norm mu underscore b dot pdf of x. The easy function is used to find out the expected value of a hidden variable. We now need to simulate the algorithm and plot its performance. Let's write the code for that. The lambdify function is used to convert a NumPy function from SymPy. Let's then declare a function run that will initialize the guess values and maximize the likelihood estimate. The code mu underscore a underscore n equals random.random times 10 and mu underscore b underscore n equals random.random are the initial guesses. Use the for loop to iterate the expectation and maximization. The code tau equals easy of xs, comma, mu underscore a underscore n, comma, mu underscore b underscore n is used to calculate the expected value of the z variable. lout.append sum of LF passing xs, mu underscore a underscore n, and mu underscore b underscore n saves the incomplete likelihood value. Out.append mu underscore a underscore n, comma mu underscore b underscore n is the save of PA PB steps. Mu underscore a underscore n equals sum of tau times xs divided by the sum of tau is used to estimate the new maximum likelihood of PA. Now, let's call the run function using out, comma, lout equals run. Let's now plot the figures using the code below. Fig equals figure. Fig.set underscore fig width 12. AX equals fig.add subplot of 121. AX.plot, passing in array of out, comma, O dash. AX.legend of mu underscore a, comma, mu underscore b with a LOC of 0. AX.hlines passing in MUA underscore true, comma MUB underscore true, comma 0, comma len of out, comma R, comma G. AX.set X label of iteration with a font size of 18. Next, AX.set Y label with mu underscore A, mu underscore B, the values of those. With a font size of 24. AX equals fig.add underscore subplot of 122. AX.plot passing an array of lout, comma, O dash. AX.set X label of iteration, font size of 18. And finally, AX.set title, incomplete likelihood with a font size of 16. Run the code and it will plot two different figures as shown on the screen. The figure on the left shows the estimates for both U of A and U of B for each iteration, and the figure on the right shows the corresponding incomplete likelihood function. The horizontal lines on the left figure show the true values we are trying to estimate. Notice the EM algorithm converges very quickly, but because each group is equally likely to be chosen, the algorithm cannot distinguish one from the other. Let's now construct an error surface to see this effect. In the code, let us call the run function using out, lout equals run. The z equals lf, passing in xs, mua underscore step, with none, mub underscore step, none, none, dot sum, open parens, axis equals 2, close parens, is used for NumPy broadcasting. And plot the figure using the subplot function as ax equals fig dot add underscore subplot of 111. We now need to unpack the container from the previous block. To do so, we use the code below. xa, xb equals zip, open paren, asterisk out, close paren. Calculate the points per iteration in red using the code ax.plot, passing in xa, xb, ro. ax.plot, passing mua underscore true, mub underscore true, next bs, is used to calculate the true values in blue. ax.plot, open paren, xa, 0, xb of 0, gx, ms equals 15, and mu equals 2. Specify the starting point in green. Once this is done, plot the graph for incomplete likelihood. Run the code, and you can see the output for incomplete likelihood. It shows the incomplete likelihood function that the algorithm is exploring. The algorithm can get to the maximizer, but since the surface has symmetric maxima, it has no way to pick between them, and ultimately just picks the one that is closest to the starting point. This is because each group is equally likely to be chosen. A hidden Markov model is a statistical Markov model in which the modeling mechanism is believed to be a non-observed, i.e. hidden, Markov process. Now, these models are known for their applications in reinforcement learning and recognition of temporal patterns, such as voice, handwriting, gesture recognition, parts of speech marking, follow-up musical scores, partial discharges, and bioinformatics. So as you can see by that wide range of use cases, hidden Markov models are widely applicable. Now here we can see how a hidden Markov model is structured. And I'm not going to read all of the variables to you, but you can see here that it's looking at the length of the observation sequence, the number of states in the model, the number of observation symbols, and many other things. Now, when we say observation, an observation is our training data in the case of machine learning. And the number of hidden states for our model is what's called a hyperparameter. Hyperparameters are those parts of a model that you, as a developer, have control over. And so here we can see for the hidden Markov model, or HMM, the underlying algorithm to it. And now there is something called an initial state. And the initial state distribution begins with a secret state. The full model with the known probabilities of state change, the matrix of probabilities of observation, and the initial state distribution is all labeled as what you see there. So building a hidden Markov model in Python is just about as simple as building a neural network model, or at least a simple one. And here we have code for how to do that. We're going to create variables to hold the states and observations, as well as our starting probabilities and transition probabilities and emission probabilities. And once we have that all set up, we can just import HMM from the HMM learn package. We're going to import NumPy. Again, you'll see importing NumPy all over the place. We're going to instantiate an instance of the multinomial HMM, or the HMM model, and tell it to have two components. And then we're going to give this model our starting probabilities and our transition probabilities and the emission probabilities. Given a known model, what's the likelihood of sequence O happening? This is a key problem that we're trying to solve with HMM, one of them. And here we can see how to do that. We import math. We're going to then run model score. In other words, scoring a model is basically the same thing as model.predict. You'll see that prediction method called different things. So in this case, we're calling it scoring the model. So you may hear people say that as well. And then we're just using math.exp or exponential in order to return that the result from the HMM in a way that we could actually read. Otherwise, it'd be very difficult to read these outputs, the model scores. Given a known model, what's the likelihood of sequence O happening? This is a key problem that we're trying to solve with HMM, one of them. And here we can see how to do that. We import math. We're going to then run model score. In other words, scoring a model is basically the same thing as model.predict. You'll see that prediction method called different things. So in this case, we're calling it scoring the model. So you may hear people say that as well. And then we're just using math.exp or exponential in order to return that the result from the HMM in a way that we could actually read. Otherwise, it'd be very difficult to read these outputs, the model scores. This is an example of an output that you might see. Now, another problem that we might want to solve is this. Given sequence O, a number of hidden states, what's the optimal model which maximizes the probability of O? Now, on the right-hand side, we see how to do that in Python. And in fact, this code kind of takes it one step further by actually generating a plot of the time series examples, where we can see time on the x-axis and the amplitude, which is assigned 16-bit integer, on the y-axis. And here we can see what exactly that looks like. This is actually a time series, a plotted time series example of the word apple. Now, this is an example of how to perform feature engineering. I'm not going to read this code to you. You can take a look at it, but essentially what we're doing here is generating features. And you can see at the bottom of the code, what we're returning are the heights and the top n number of peaks. And here is an example of that. So what the plot shows are the peak locations at certain frequencies. So this is actually a visualized output of the code that you just saw. Now, training in HMM is called estimating the model in this case. So here we're going to create a Gaussian HMM. We're going to train it on our data, and then we're going to run a number of predictions using our test data. Now, breaking up a data set into a training set and a test set is very common, especially in supervised algorithms. If you're not too worried about time, then this is a perfect method for using a single data set for both training and then testing models on. So using HMMs in speech recognition, what we might want to do, which you can see on this slide, is letting us represent the speech as a sequence of observations. So we can use an HMM to model some unit of speech called a phone or a word. Those are units of speech. And we can concatenate those units into larger units. Just like you can think of how a conversation has parts to it, where we can look at each of those parts individually. This does effectively that same kind of thing, where we can take smaller parts and concatenate them into larger parts. Let's look at some model topologies. Well, one model topology is called ergodic, which is fully connected, where each state has a transition to every other state. And you can see that in the diagram on the right, where every circle connects to every other circle. So this is what we call fully connected, which is something you'll hear, a term you'll hear with neural networks. And on the bottom, we can see what's called left to right. In other words, transitions only to states with a higher index than the current state. And these inherently impose a temporal order, and they're most often used in speech. And you'll see applications of this left to right in other things as well. For instance, DAGs, or directed acyclic graphs, are graphs that will go in one direction and they cannot go backwards. And that's kind of what is happening here. Only these can also loop back on themselves. But either way, you do not go backwards. You're only going forwards. And that is why they can inherently impose temporal order, because we never move backwards in time as people. We just move forwards in time. Hence, they're most often used for speech, as opposed to the ergodic, which are fully connected to each other, which theoretically means that you could go back to where you started. So typically the left to right HMM, or hidden Markov model, is used to model a phone. Because as I mentioned earlier, speech does not go backwards. We don't speak in reverse, we only speak forwards. And also a phone's pronunciation varies in different phases. So an example of a phone HMM topology is below. And we can see the transitions for line 1. We go from 0, and then we can transition to 1. Or we can transition basically back to itself of 0. State 1 can transition to itself, or it can transition to state 2, and the same thing with state 3, and then state 3 is basically the end, at least for the example that you see here. So now we have something called an HMM, Gaussian Mixture Model, or GMM for short. Now you can use Gaussian models to model HMM states. For example, you can use 39 Gaussians, which corresponds to the dimension of the MFCC. Now a state might have different GMMs, and states can also share the same GMM. So here's a real example of that, where phone 61 maps to I-12, where the second column are basically the states, and then the third column is the GMM PDF. Now there's different types of HMMs as well. On the left here, we see there's the whole word HMM. We also have a context-independent phoneme HMM, and then finally the context-dependent triphone HMM. Now there's different types of HMMs as well. On the left here, we see there's the whole word HMM. We also have a context-independent phoneme HMM, and then finally the context-dependent triphone HMM. For decoding, the problem is that we want to find a state sequence which maximizes the probability of an observation sequence. And the solution to that is a Viterbi algorithm. For training, the problem is that we want to adjust the model parameters to maximize the probability of observed sequences. And for this, we can use a forward-backward algorithm. Welcome to the spectrum analysis demo. In this demo, we'll understand the spectrum analysis using the different parameters of signal, including frequency, amplitude, time, and others, and also how the signal is affected based on these parameters. Before getting into the code, let's first understand what exactly spectrum analysis is. Spectrum analysis is the process of determining the frequency domain representation of a time domain signal. It also commonly employs the Fourier transform. So to do this, let's first import the packages and dependencies required for this demo. First, import the sin, linspace, and pi packages from NumPy. NumPy.sin will be used to print the sine of an angle. Next, import plot, show, title, xlabel, ylabel, and subplot from PyLab. These packages will be useful for plotting the graph signal and displaying it. Now, import FFT and arrange from SciPy. FFT stands for Fast Fourier Transform, which is a computing algorithm that provides an accessible introduction to Fourier analysis and its applications. Once all the packages are imported, let's write a function that plots a single-sided amplitude function. In other words, the plot spectrum function. It takes two parameters, the time domain and the frequency domain. Here, n equals len y is used to declare the length of the signal. K equals arrange n. The range function returns an ND array object containing evenly spaced values within a given range. T equals n divided by fs calculates the time interval. FRQ equals k divided by t declares the two-sided frequency range. FRQ equals FRQ of range n2 is used to calculate the one-sided frequency range. Y equals FFT of y divided by n is used to compute and normalize a fast Fourier transform. y equals y of range n2 is used to compute and normalize the one-sided frequency range. Now, let's plot the spectrum using the code below. Plot FRQ dot, or rather comma, ABS of y, R. X label, frequency in hertz. Y label is the Y frequency. Since we have already declared the function to plot this spectrum, let's now declare the signal parameters. Fs is the sampling rate. Ts is the sampling interval. T is the time vector. And F is the frequency of the signal. Once the parameters are declared, we plot the signal using the code below. Subplot 2, 1, 1. Plot t, y. X label, time. Y label, amplitude. Subplot 2, 1, 2. Plot spectrum y, fs. Show. Here, the X label and the Y label are the parameters, time and amplitude, respectively. The show function is used to display the plot. Run the code and you'll see the output. The two signals represent two different parameters. The first graph shows amplitude versus frequency, while the other graph shows the double-sided frequency signal. So, key takeaways of this module. First off, you now have an understanding of what's an audio signal. We then looked at the parameters of an audio signal. You saw how frequency affects a wave. You learned about different types of signals, digital and analog. We discussed how to perform signal sampling. We then discussed feature extraction techniques for an audio signal, and you saw how to do that with code. We discussed template matching and performed acoustic modeling and language modeling, and then dug in deep with hidden Markov models. Thank you. Welcome to Module 3, Speech to Text. We have two main learning objectives in this module. First is implementing speech to text in Python, and secondly, data visualization and exploration. First, let's start off with discussing understanding the problem statement. So here is our problem statement. We want to use a speech commands dataset to build an algorithm that understands simple spoken commands. So what is in this speech commands dataset? Well, firstly, it includes 65,000 1-second long utterances of 30 short words by thousands of different people. It contains WAV or WAV audio files, each containing a single spoken English word. The audio files themselves are organized into folders based on the words they contain. And the goal of this was to gather examples of people speaking single word commands rather than conversational sentences. So you can imagine this being used in a system that is command based, something like an Alexa or Google Home or a Siri. So the first thing that you want to do is import the libraries. But before we even talk about that, let's talk about the package that we're going to use, which is Librosa. So Librosa is a Python package for music and audio analysis. It provides the building blocks necessary to create music informational retrieval systems. And so with any Python application, the first thing that we need to do is import all of the libraries which we need. And we need a few. We need to import pandas and numpy, also a number of different parts of the scipy package. And then finally, we're going to import Librosa and also the PCA, which is principal component analysis functionality from scikit-learn or sklearn's decomposition. Welcome to the speech-to-text modeling demo. In this demo, we'll understand how to build our own text-to-speech model using Python. As a first step, go to the Start menu of your window and open the Jupyter Notebook. Once the Jupyter Notebook is initialized, you can see the link redirected to the browser. Click on New and then Python 3 to create a new Python project. Let's rename this notebook to Speech-to-Text Model. Now, let's see how to implement this task. First, we need to import all the packages that are required to perform this task. Import OD in Librosa. Import ipython.display as IPD. Import matplotlib.pyplot as PLT. Import numpy as NP. Import wavefile from scipy.io. And import warnings, which uses the filter warnings function that's used to ignore the unwanted or unnecessary warnings. The data exploration and visualization, which we'll perform, will help to understand the data as well as pre-processing steps in a better way. Now, let's visualize the audio signal in the time series domain graph using the code as shown on the screen. We specify the path of the audio file. Ensure that the complete path of the audio is specified, otherwise the code won't work. We use the librosa.load function to load the audio file. We also use the plt.figure function to specify the size of the figure that will show in the Jupyter Notebook. Now, we set the title, X label, and the Y label for the output graph. Using the plot function, we now display the graph. Run the code, and you can see the output as shown. Let's now look at the samples of the audio signals. To do so, use the ipd.audio function and run the code. You can see the output is shown on the screen. To print all the samples, let's use the print function and run the code. The output shows all the samples of the audio. Now let's resample it to 8,000 Hz since most of the speech-related frequencies are present at 8,000 Hz. To do so, we use the librosa.resample function where we pass the sampling rate generated. We then use the ipd.audio function where we specify the rate as 8,000. Run the code, and you can see that the audio output comes to be similar with different sampling rate. Now, let's understand the number of recordings for each voice command. Just loop through each WAV file in the folder, and you'll be able to see the number of recordings for each voice command. The screen showing the code, or shows the code rather, required to implement this. Let's examine the code step by step. We first specify the path of the audio and produce labels using the os.listdir function. Then, we try and find out the count for each label and plot the bar graph for each of these. To find the count of each label, we declare an array called number of recordings, or no underscore of underscore recordings, and use a for loop that will iterate for each label along each of the labels. The variable, or rather waves variable, stores each value that ends with .wav. And then we calculate the number of recordings by calculating the length of the wave function. Now, to plot the graph, let's declare the figure size and calculate the index using the arrange, A-R-A-N-G-E, function as shown on the screen. We then pass the index and the number of recordings as the parameters to the bar function. It will consider both the parameters as the x and y axes. Let's now label the x-axis and the y-axis using the x-label and y-label functions respectively, as shown. After specifying the title for the bar graph, let's plot the graph using the show function. Now run the code. Let's also specify all the labels required. And let's now see how to calculate the duration of the recordings. To do so, we must first declare an array called duration of recording. We iterate along the labels and calculate waves using the os.listdir function that calculates all the labels that ends with the .wav format. We then calculate the sample and sampling rate using the read function, which reads the file and calculates the samples, which are later appended using the append function. Lastly, we use the hist function to print the histogram. Run the code and you'll see the output in the form of a histogram as shown on the screen. Let's now see how to perform pre-processing, which includes resampling and removing shorter commands. Here, we declare two arrays as all underscore wave and all underscore label, and we extract the labels with a .wav extension. The librosa.load function is used to load the audio file with the specified label and the sampling rate. Then, we use the resample function, where we resample the labels based on the samples and the sampling rate. A condition is also specified, where if the samples are equal to 8,000, we append all the samples to the all wave array, and then append all the labels to the all label array. Run all the code cells, and you'll see that the output comes to be the list of labels present. Now, let's convert the output labels to integer encoding. To do so, we import label encoder from sklearn.preprocessing. To perform the encoding, we call the label encoder function and transform all the labels using the le_fit_transform function. We also use the list function that calculates the list of classes and stores it in a variable named classes. Now, let's convert the integer encoded labels to a one-hot vector since it's a multi-classification problem. To do so, we import np_utils from keras.utils. And to convert the integer encoded vectors, we use the nputils to categorical function. Let's now reshape the 2D array to 3D, since the input to the conv1d must be a 3D array. This can be done using the reshape function, as shown on the screen. Now, let's split the entire dataset into training and validation sets. Next, we'll train the model on 80% of the data and validate on the remaining 20%. These are our training and validation sets respectively. To do so, we import train test split from the sklearn.model_selection module, and then use the train test split function as shown on the screen. Run all the code cells. Now, the major step in this process is actually building and implementing the model using the Keras functional API. You can see the code on the screen. Let's examine this code. We start by importing dense, dropout, flatten, conv1d, input, and max pooling 1d from Keras layers. We then import model from Keras models. We import early stopping and model checkpoint from Keras callbacks. And finally, we import backend as k from Keras. Then, we use the import function to define the shape. We have defined the first, second, third, and fourth conv1d layers using the conv1d function, max pooling 1d function, and the dropout function. We then use the flatten function to define the flattened layer. Similarly, we use the dense function to declare the dense layers 1 and 2. Once the dense layers are defined, the output of the dense function is stored in the outputs variable, which is based on the labels and the activation value. And then the inputs and outputs are passed as parameters to the model function to create a model. Now, run all the code cells in case we didn't do it earlier. Next, let's calculate the cross entropy. To do so, we use the mode.compile method, which takes the loss value, optimizer value, and the metrics as parameters. We define the early stopping and model checkpoints using the respective functions. Early stopping and model checkpoints are the callbacks to stop training the neural network at the right time and to save the best model after every epoch. Both the functions require verbose value as parameters, based on which the callbacks are performed. Now, let's write the code for model fitting, where we use the model.fit function, which calculates the history based on the epochs, callbacks, batch size, and the validation data. Run the code, and you can see the output that shows the training samples, validated samples, and epoch value. This may take some time. The process ends here, since the model building may take a lot of time, potentially 3 to 4 hours, depending on the power of your CPU. Now, we have successfully completed the process of speech-to-text modeling. Data visualization. Data visualization helps us to understand the data as well as the pre-processing steps in a better way. Here we'll see two examples. The first is the input spectrogram, which shows us the frequencies, and the next is the MFCC, or Mel Frequency Cepstral Coefficients. So to do data visualization, we start off by reading a file. So we're going to give our code the input audio path, or for the input path for the training data that we're going to use. Going to give it a file name. We're going to then separate out the sample rate and the samples using the next lines of code. So next what we need to do is define a function that actually calculates our spectrogram. So you can see the code here on the slide, and you also have code available to you. But essentially we're going to create a method called log specgram, and it's going to take a number of arguments. First, we're going to give it the audio. Next, we're going to give it the sample rate. Then we'll have a window size, and by default, we're going to set our window size to 20. We then give it our step size, which by default will be 10. and then we'll give it our EPS, which is 1 to the negative 10. Now, next we're going to calculate the number per segment, or n per seg. Going to calculate our overlap after that. And then we're going to get our frequencies times and our spec from the signal.spectrogram, giving it the audio, the FS or sample rate, the window, number per segments, number of overlaps, detrend, all of that. And what this method is going to return are our frequencies, our times, and from the NumPy package, a log of our spec. And what we're going to see here is that actually our frequencies are going to be in a range of 0 to 8,000 according to the Nyquist theorem. Data visualization. Now that we are taking the logarithm of the spectrogram values, it will make our plot much clearer. Moreover, it is strictly connected to the way that people hear. We need to assure that there are no zero values as input to our logarithm. So let's look at this example code. Well, to plot this, pretty easy. We have frequencies, comma, times, comma, spectrogram equals the log underscore specgram. And we pass that the samples and the sample rate. Then we can plot it using plt.imshow and passing it the spectrogram.t, aspect equals auto, origin equals lower, and the extent equals times.min, comma, times.max, comma, frequencies.min, and the frequencies.max. And so here on this slide, we can see the output of this visualization. So at the top, we have our raw wave. And at the bottom, or the second chart, we see a spectrogram from this exact same wave file, or the spectrogram version of this exact same audio file. Now next, we're going to calculate our MFCC. And you can calculate the Mel power spectrogram and MFCC using the Librosa Python package. And this is one of the reasons that we chose to use the Librosa package in the first place. And the code that you can see here on the slide does come from the Librosa demo code. So I'm not going to read all of this to you, but essentially what this is going to do is do everything that we just said, which is calculate that Mel power spectrogram and MFCC using the Librosa Python package. But just to go through the comments here, what we're going to do is use the Mel spectrogram function from the Librosa.feature package, giving it our samples, sample rates, and the number of the n mels. And we're going to set that to 128. Next, we convert it to a log scale, and we use the peak power, or max, as the reference. And then we can plot it out using the PLT methods that you see there on the slide. And this is the output, a nice pretty chart showing what a Mel power spectrogram looks like. Now in classical MFCC, or rather in the classical way of doing this, MFCC or similar features are taken as the input to the system itself instead of the spectrograms. However, in end-to-end systems, the most common input features are probably the raw spectrograms, or the Mel power spectrograms that we just saw. And on the right hand of this slide, it shows you how to actually produce the MFCC. And again, it's a method from the Librosa.feature, or the feature portion of the Librosa package, rather. And so what we're going to do here is basically just pad on the first and second deltas. And then finally, we're going to create the plot itself. So everything that you see here on the slide, this PLT dot, whatever comes after that, is part of the actual plotting of itself. And then we also call Librosa.display.specShow, giving it that delta2 underscore MFCC that we had created before. And now here on the slide, we can see what an MFCC looks like visualized, where time is on the x-axis and the MFCC coefficients are on the right axis. And then we do have a legend on the right-hand side that tells you what each of these means as well. Now here on this slide, we can see a spectrogram in 3D, and we can actually produce these with just a few lines of code. We set up our data, we then create our outlook, and then we can just plot this chart out. Pretty straightforward. And if you're using something like Jupyter Notebook to do this, then you can see all of these plots in line. And then on the left is a spectrogram of the word yes in 3 dimensions. The 3 dimensions being the log amplitude, the frequencies, and time. So a very useful visualization of seeing a spectrogram of a single word. Now, one of the things that you might need to do is removing silence, because sometimes the words are short, and within that word there can be a lot of silence in of itself. Or if someone is speaking a word out loud, for that single word, they might have a pause as they're saying the word itself. So something called a descent VAD, or voice activity detection, can reduce our training size a lot, accelerating training speed significantly. In other words, it removes the silence that's present in those words. Therefore, we have smaller files that we're trying to train our models on, therefore accelerating our training speed. The way that we can do this is shown in the code on the right-hand side. So what we're going to do here is plot the same thing again, together with guessed alignment of the Y, E, and S graphemes. In other words, each of the written characters, we're calling a grapheme here. And then the rest of the code shows exactly how to do that. And here's what that looks like here. At the top, we can see the raw wave of the word yes. And at the bottom, we see, again, another spectrogram of that with the noise removed from it. And if you look back at the previous chart, or the previous spectrogram, they look quite different. So here we have the shades of green and yellow spread out, and you can see at the bottom where the Y, E, and S are. And this looks very different than the previous slide that we had. So this is with the noise removed from it. Pretty neat. One of the things that we might also need to do to reduce the dimensionality of our data is to resample the recordings. And the reason that we want to reduce the dimensionality of our data is effectively to make training a lot faster, and also just to reduce the total amount of data that we have to feed into a model. Sometimes models like a huge amount of data, and sometimes because of the sheer cost of computation to do that, and you can imagine with audio, we could have audio files can be enormous, and we want to reduce the size of those files as much as possible. And then we want to reduce the dimensionality of our data. And on the right-hand side, we have a method for calculating an FTT, or a fast Fourier transform, that is one way of performing the resampling. So it's pretty straightforward. We just use the linspace method from NumPy, and the linspace and the absolute value methods from NumPy, and a little math, and then we can actually create a fast Fourier transform that we can then use. And in these charts, we can see the FFT, or fast Fourier transform, sampled at 2 different frequencies. At the top, we have the FFT of the recording sampled with 1600 hertz, or 16,000 hertz rather, excuse me. And the bottom chart has the FFT of the recording sampled at 8,000 hertz. So you can see the difference there in frequencies, where with the 8,000 hertz, the frequency ends at 4,000, whereas with the 16,000 hertz, it really ends, well, the chart itself ends at 8. But if we look at it, right, in the sample, they both end about the same place, which is the 4,000. So the 4,000 frequency looks like what we want to use for our target there. And this is why we want to use data visualization, or really how we can use data visualization to help us to figure out how we should handle the underlying data itself. So data exploration is basically exactly as it sounds. It's just a way for us to explore the data that we have. So in this slide, on the left-hand side, we have a chart showing the number of recordings in a given label. So you can see the words on the x-axis from left to right. You see bed, bird, cat, dog, down, etc. And also, we can see the number of recordings that we have of each of these words in the data set. So it looks like the max of any of these words we have is getting pretty close to 2,500. It might be around 2,400. Some of the other words we have around maybe 1,600, 16 to 1,700 samples of each of these. And on the right-hand side, we just have code that you can use to produce this plot. And again, we're just exploring the data set that we have to see how much data are we working with. How many of each recordings do we have for the words? We can use these to try and figure out how many more training examples might we actually need to get. So for instance, if you think you're going to be using bed a lot more, then maybe because in this training set we only have about 1,600, 1,700 samples, maybe you want to get more. And in this way we can see that yes, we definitely want to get more for bed, if you were going to use that word potentially a lot in your application. Data exploration. Let's look at the code to see the number of recording lengths. First, we start by saying num of shorter equals 0. And then for direct in dirs, waves equals f for f in os.listdir, join the train audio path, comma direct, if f ends with .wav. Then for wave in waves, sample rate, comma samples equals wavefile.read. Passing in the train audio path plus direct plus a / plus wave. Now if the samples.shape of 0 is less than the sample rate, then the num of shorter plus equals 1. Finally, we print the number of recordings shorter than 1 second, and we add the number to that. And then at the very bottom, we can see what the output of this piece of code looks like. And what it says is number of recordings shorter than 1 second is 6,469. And essentially what we're doing here in this code is we're looping through all of the wave files within the directory that we were listing. That's what that os.list directory does. It goes through and says, hey, give me all of the files that end with WAV, and then looks to see how long each of these files is. Model architecture for this problem. And on this slide, we can see the distribution. It's a histogram of the recordings for seconds. So a lot of them are between 0.9 and 1 second, about over 20,000 of them. And then we have a number that are also below that as well. And then on the right-hand side is the code to actually produce this distribution that you see here on the slide. And now this may or may not be a problem for your application. Maybe the words that are less than 1 second are smaller words like a, and, the, who knows? That would be something that you might want to look at. Maybe this is not a problem at all. But at least by visualizing it, we can then determine, do we need to look even deeper into the data that we're going to be using for our models? Next, we're going to look at processing the audio waves. And essentially what we'll do here is 2 steps. You read the audio waves, and then you use them. First by resampling, and then you remove these shorter commands of less than 1 second. So here we've determined we don't want any of these things that are going to be less than 1 second because we want commands, and not many commands that we might use are going to be less than 1 second in length. And then on the right-hand side, you can see we're using TensorFlow's speech recognition challenge audio in order to do all of that, to perform the resampling and then removing the shorter commands. And then finally here on this slide, we look at processing the audio waves first by converting the output labels to integer encoded. Then we convert those integer encoding labels to one hot vector since it's a multi-classification problem. And then finally, we're going to reshape the 2D array to 3D because the input to the convolutional network needs to be a 3D array. Now, the next thing we need to do before getting into our modeling is splitting the training and validation sets. And this is a classic technique in statistics and machine learning, where you take your entire data set and you split up some percentage, you hold back some for training and then some other for test. And the reason that you do this is because you train the model on, let's say it's 80% of the data, and then you use that test set to then perform predictions. Now with the test set, you already know what the model should be predicting, and that is why it is the test set. You already know what the output is. And so in this way, you can tell whether or not your model, your trained model, is actually performing well on data, in other words, on samples that it hasn't seen. The ultimate goal with machine learning is we want our models to be able to generalize to other data later on. If the models only work with the training data set that you've provided, then they are not going to work in real life applications. So in this way, by splitting our data into training and test sets, and training on the training, and then obviously testing on the test set, then we can see, can our model generalize well, which is again what we want. So on this slide, we can see how easy it is, just about 3 lines of code in order to split our data into training and validation sets. And here we're going to train the model on 80% of the data and validate on the remaining 20%. And again, this is a very standard technique when doing supervised learning, or supervised machine learning rather. And to do it, we can just use the train test split different methods from scikit-learn's model selection package or features. Welcome to the data exploration and visualization demo. In this demo, we will visualize the audio files and analyze the parameters of a file. As a first step, go to the Start menu of your window and open the Jupyter Notebook. Once the Jupyter Notebook is initialized, you'll see the link redirecting you to a browser. Next, click on New and then Python 3 to create a new Jupyter Notebook using Python 3. Let's rename the file as Data Exploration and Visualization. Now, let's see how to implement this project. First, we need to import all of the necessary packages. We'll import OS, import Librosa, this is for audio processing, import ipython.display as IPD, import librosa.display, import matplotlib.pyplot as PLT, import numpy as MP, import wavefile from scipy.io. This will be used for audio processing. And then import warnings and filter the warnings using the filter warnings function. What this does is it will ignore any warnings that may come up further on in the code. Now, the data exploration and visualization is used to help us understand the data as well as pre-processing steps in a better way. So let's visualize the audio signal in the time series domain graph using the code as shown on the screen. What we do here is specify the path of the audio file. Now when doing this, ensure that the complete path of the audio file is specified. Otherwise, the code will fail. We use the librosa.load function to load the audio file. We also use the plt.figure function to specify the size of the figure, which is the plot that we will see inside of our Jupyter notebook. Now let's pass the sample and sample rate as parameters to the librosa.display.waveplot function. This will generate the waveplot for the audio signal. Run the code and you can see the output of the waveplot as shown on the screen. Now, let's look at the sampling rate of the audio signals. To do so, use the ipd.audio function and run the code. You can see the output is shown on the screen. To print the sampling rate, let's use the print function. And then run the code. You can see the output gives the sampling rate as 22,050. From the above, we can understand that the sampling rate of the signal is 22,050 Hz. Let's resample it to 8,000 Hz, since most of the speech-related frequencies are present at 8,000 Hz. To do so, we use the librosa.resample function, where we pass the sampling rate generated. We then use the ipd.audio function, where we specify the rate as being 8,000. Run the code, and you can see that the audio output comes to be similar with different sampling rates. Now, let's understand the number of recordings for each voice command. Just use a for loop to get each WAV file in the folder. And now you'll be able to see the number of recordings for each voice command. The screen shows the code required to implement this. Let's examine the code step by step. We first specify the path of the audio and produce labels using the os.listdir or list directory function. Then we try and find out the count for each label and plot the bar graph for each of these. To find the count of each label, we declare an array called no of recordings, or number of recordings, and use the for loop to iterate over these, which will iterate for each label along each of the labels. The waves variable stores each value that ends with .wav, and we then calculate the number of recordings by calculating the length of the wave function. Now to plot the graph, let's declare the figure size and calculate the index using the arrange, A-R-A-N-G-E, function as shown on the screen. We then pass the index and the number of recordings as the parameters to the bar function. It will consider both the parameters as the x and y axes. Let's now label the x-axis and the y-axis using the x-label and y-label functions respectively, as shown. Also, specify the title for the bar graph. Now let's plot the graph using the show function. Run the code. Oops, we have an error that says file not found. Let's check if we have specified the correct file path. copy the file path from the local system and paste it in order to avoid errors. And then run the code again. You can see the output in the form of a bar graph, with the x_axis and y_axis specifying the labels which you have previously defined. Here, we have successfully completed the process of data exploration and visualization. All right, so let's now look at model architectures. So the model architecture that we're going to use for this problem is here. And we're going to build a speech-to-text model using a convolutional one-dimensional network, or conv1d is what it looks like in TensorFlow. So this conv1d is a convolutional neural network which performs the convolution among only one dimension. And here on the right, we see the model architecture, and we're going to be using something called Keras for the functional API. And Keras is basically an API that sits on top of TensorFlow that makes it very easy to use TensorFlow. And what that looks like here on the right-hand side is we have our input that gets fed into our convolutional neural network, which goes into the max pooling, and we're going to do that 4 times. We then produce this dense neural network, and then finally we have our output. Here, we are showing the code that is going to produce the model architecture for our problem. And what we're going to do is use a number of functions and features of Keras. So on the left-hand side, we first need to import everything we need. So we say from keras.layers, import dense, dropout, flatten, conv1d, or convolutional one dimension, input, and max pooling 1d. Next, from keras.models, we import model. After that, from keras.callbacks, we import early stopping and model checkpoint. And then finally, from Keras, we import backend as capital K. So next we define our inputs. And here the inputs equals input shape given 8000, 1. Next, we start defining, or we define a layer. And so we say conv equals conv1d, and we pass in the parameters at 8, 13, padding of valid, activation equals relu, and strides equals 1. Then we have our inputs. Next, we say conv equals max pooling of 1d, giving it 3 in our conv from before. Next, we add the dropout of 0.3. Next, we add another convolutional 1d with the parameters 16, 11, padding equals valid, activation relu, strides equals 1 in conv, so almost exactly like we did before. Next, we set max pooling 1d, 3. We have a dropout of 0.3 on the following line. And then after that, we have conv1d, this time passing in 32, 9, with the same valid padding, relu activation, and strides equals 1, and passing in our conv. The code continues on the right-hand side of the slide, where we add a max pooling 1d of 3, a dropout, again of 0.3. We add another convolutional 1d, this time passing in 64 and 7 as the initial parameters. We add another max pooling 1d. We have a dropout of 0.3. And now we finally flatten. And then we have a dense layer of 256 with the activation of relu. We have another dropout of 0.3. We add another dense layer of 128. We add our dropout again of 0.3. And then finally, we define our outputs as dense with the length of our labels. We set the activation to softmax. And then finally, we define our model very easily, just saying model equals model, passing in the inputs and the outputs. And so once we have that, what we do is we define our loss function to be a categorical cross entropy because this is a multi-classification problem, meaning multiple words could go in and we need to classify what each of those words is. Next, we have early stopping and model checkpoints. And these are the callbacks to stop training the neural network at the right time so that we can save the best model after every epoch or after every really training session, if you will. And then finally, we need to train the model on a batch size of 32 and then evaluate the performance of it using our holdout set. And then finally, we're going to create a diagnostic plot, which helps us to understand the performance of the model over a period of time. And the way that we do that is using the pyplot method from matplotlib. Write a couple lines of code, which you can see here. We're going to then load the best model and produce the chart, which looks like this. And so we can see that the difference between the test set and the training set is not too bad at all. So this network is actually doing quite well with the architecture that we have given it currently. Model architecture for this problem. So here we want to define the function that's going to predict the text for the given audio. And that code is here on the right-hand side. So what we do is we define a predict function which takes as input an audio. We then say probability equals model.predict, passing it in the reshaped audio with the parameters 1, 8001. We get the index, which equals np.argmax of the first item in our object that we defined earlier, and then we return the index of the classes. Now next we're going to make predictions on our validation data, and the code is here for that. And ultimately we're going to print out the samples. Next we want to create a script that prompts the user to record their voice commands. And you can record your own voice commands and actually test it on the model that you've produced. Now to do this, we're going to use two different Python packages. The first is called sound device and the next is called sound file. And you can just install these using pip install sound device and sound file. And then after a few lines of code, what this code is going to do here is it's going to use a sample rate of 16,000, something that we saw before in one of the charts. We're going to give it a 1 second. We're going to actually feed it in our file and then print start. And what this is going to do is it's going to record the input and then print out end. It's going to wait a second and then it's going to write out a file for us. So now let's read the save voice command and convert it to text. And to do that, again, just a few lines of code. Luckily in Python, doing a lot of this stuff isn't really a huge amount of code to do. We want to list all the files in our directory, get a file path, read in these voice commands, actually from the audio samples that we have. So we're going to load that in using the Librosa package. We then resample, and then we create we have that audio, and then we run predict on those samples that we've created. And that is the end of Module 3. So by now you have an understanding of how to implement speech to text in Python and the how and why behind data visualization and exploration. Thank you very much. Module 5, Multilingual Speech Processing. After completing this lesson, you should be able to understand multilingual speech, issues involved in multilingual speech, and different language speech synthesis techniques. Part 1. Understanding multilingual speech. A multilingual speech recognizer is able to transcribe speech from different languages. It can identify the language used, as well as word sequences uttered by the speaker. And it can identify language and word strings in parallel. Now, a more effective way is to identify the language using a language identification system prior on homogeneous acoustic segments. and then decoding the word strings with the appropriate language-dependent recognizer. In other words, instead of having just one model that can understand multiple languages, you identify the language first and then feed it into the appropriate language model. Now, existing systems have been developed for specific domains and a restricted number of languages. These require large amounts of annotated language-specific corpora. For example, Google's Speech API can recognize 70 different languages and handle 50 different accents and dialects. Apple's Siri, however, can understand 21 languages and 21 accents and dialects. Part 2, issues in multilingual speech. So there are a number of issues that arise with multilingual speech. The first is the differences between languages, because all languages are fundamentally different, and combining the features from different languages into one framework or one model is actually quite difficult. Next, scripts and fonts. Different languages have different character types. And there is also a varying relationship of grapheme to phoneme relationships between these different characters. And sometimes you can have complex rules and many exceptions that you have to deal with as well. Thirdly is romanization and segmentation. Some sentences are written in strings of characters without any spacing whatsoever. Therefore, segmentation of speech data may actually be required before you can do anything with it. Fourthly, prosodic structure. The prosodic structure of words varies across languages. Some languages are rather pitch accent, and others use stress. For instance, English shows exceptionally simple morphological structure, whereas German and Japanese have very rich, or rather are very rich morphological languages. Now, morphological rich language has rapid growth of the number of word forms occurring in a given test. That's what we really mean by that. Now, this does have an impact on the recognition quality. And even in addition to all of that, you can have out of vocabulary words as well. In other words, words that people are using that were not in part of the vocabulary used to train the models in the first place. And then finally, we have morphology. Now, in linguistics, morphology is the study of words, how they're formed and their relationship to other words in the same languages. And here it analyzes the structure of words and parts of words, such as stems, root words, prefixes, and suffixes. Some of these things we've seen in previous modules. Now, morphology also looks at the parts of speech, the intonation and stress, and the ways context can change a word's pronunciation and meaning. Morphology absolutely changes from language to language. In fact, the basic structure of sentences varies greatly from language to language, and this can make it very difficult to have a single model that works for multiple languages. Ultimately, you could have a single model that is rather large, and actually the time it would take to even use that model might be way too expensive to be used in the first place. Part 3, different language speech synthesis. Now, while there are challenges to creating a multilingual system, there are definite benefits to it. The first is in terms of complexity. When using a multilingual system, you can reduce the number of parameters and the complexity of the system by sharing codebooks and joining parameters across languages. And next, it can also be fast and efficient because you can essentially bootstrap recognition systems with new languages, even if only a small amount of training data is available. And what is meant by that is that you can use work that you've already done and then build on top of that work with a new language. And in order to do that, what we need to do is share information between acoustic models. And there's 6 parts to that. First is just the general principle, and that is to use a neural network's hidden layers to learn a multilingual representation. Second, the hidden layers. The hidden layers are multilingual shared between languages. We have our output layers, which is actually a monolingual language specific. 4, we can use what's called the hat swap technique, which uses a network with multilingual hidden representations directly in hybrid DNN and HMM systems. And DNN stands for Deep Neural Network, and HMM, something we've seen before, which is Hidden Markov Model. We can also use block softmax to train a network with an output layer for each language, but actually share the hidden layers within the network itself. And then finally, we can use a bottleneck hidden layer, which is a multilingual bottleneck, which uses a what's called a bottleneck hidden layer, which is trained in a multilingual way as features, and use these rather as features for either a GMM or a NN based system. And GMM stands for a Gaussian mixture model, and NN stands for neural network. So here's an example of a hat swap architecture. We start off on the far left with our base architecture, which is stacked RBMs trained on, in this instance, Polish. And an RBM stands for restricted Boltzmann machines. That's one thing that we can use. So on top of this base network, we then have on the other 4 parts a DNN that is trained on a specific language. So we start off with Czech, then German, Portuguese, and then finally we fine-tune our DNN or deep neural network on Polish. So here this shows how we can keep using our base neural network architecture and then just fine-tune on different languages to then produce a multilingual network. And again, this is called a hat swap architecture, which was created in 2013. Next, we have block softmax. So in block softmax, we train one network for all languages. And what this does is it separates output layers or produces separate output layers for each language, but shares the internal hidden layers. In this technique, each training input is propagated forward to the output layer of the corresponding language, so that only that output layer is used to compute the error used to train the network for that input. Also, since the hidden layers are shared, they must learn features relevant to all of the output layers, which again in this case, or this instance, are different languages. And you can view block softmax as a parallel version of a hat swap. That's one way to look at it. And here's an example of this block softmax architecture. So in the beginning, we are inputting at the very bottom of our diagram here 4 different languages for training or testing samples. We have our input layer, which is composed of a window of acoustic feature frames. We have many hidden layers, which are actually used for all of the languages. And then finally, at the very top, we have those different output layers that I was just mentioning. One output layer for each language. And again, all the languages are sharing the internal hidden layers, but then we only have one output layer for each of the individual languages. Now this diagram shows an example of a multilingual bottleneck features architecture, where again we're inputting multiple languages, English, French, German. They share the hidden networks internally, and then we have the output layers, one for each language. So very similar to the hat swap architecture. And now in this chart, we see the outcome of multilingual bottleneck feature experiments. And what this is showing is GMM-based acoustic models, the results of them. And GMM here again stands for Gaussian mixture model. A little explanation here might be warranted since there is a lot going on right here. So MFCC is something that we've seen before, which is the Mel frequency substral coefficients. And what they collectively make up is something called an MFC, which is a representation of the short-term power spectrum of a sound based on linear cosine transform of a log power spectrum of a non-linear Mel scale of frequency. So that's a lot to take in, but ultimately what we are trying to do is best represent the sounds that are input to the system. For example, if we are trying to perform audio compression, then we do not want to lose, or we want to lose as little sound as possible when we are performing that audio compression, because ultimately what is output by that system really should be as close to what was input as possible. And that's what we're going for here, is to have a really good representation of the sound. Although in this instance, we're not trying to compress the audio, we want to input audio into the system, run it through our network, and then understand what language is going to be output, or be able to create an output sound that best represents that went into it. In other words, if we have German going into our system, we want German coming out. We don't want German going in and then English coming out. And so this chart is just showing some results of training these different networks. On the left, we have our bottleneck, and on the right, ultimately, we have a mismatched acoustic environment actually being output. Part 4, encoding characters. So character encoding is an important part of the data recognition, data manipulation, and in displaying the components of multilingual information access. And we use this to yield a more compact model representation with reduced computational costs. And that's important because the larger the models that we produce, the longer it will actually take to use them, and the more cost is then required to actually use them. Next, character sequences can be computed for any language without requiring a separate language identification model. So one of the things we spoke about earlier was maybe it would be more efficient to figure out what the language was first and then run it through the appropriate language model. But here, what we want is a single model that can be used for multiple languages instead of having to train multiple models. And that's important because when you're talking about deploying these systems into production, the more models that you have, the greater the complexity in your system, which then creates just a lot more support overhead and also a lot more cost for running the system itself. Now, also, character encoding is important because we can use it to automatically predict the correct character sequence for the target language of each utterance, and utterance being the spoken words themselves. And then also it can eliminate the duplication of output symbols that occur in multiple languages. So in other words, each language, ultimately, we're going to get these output symbols, and we can reduce the duplication of those using techniques like character encoding. So here's an example of how to do character encoding. The thing to keep in mind here is that once these sequences are generated, the next step is to encode each of the characters. And what we are going to see output is a sequence of numbers. Now, one of the things that you may already understand is that computers do not work with letters, they work with numbers. So this is a technique effectively to turn all of our letters into numbers so that then the computers can work with them. And this is rather straightforward to be able to do. We can define a method called encode sequence, write a few lines of code here, append to effectively a list, and then return that. And then we can use our method inputting the sequences that we have. And here is an example of the output. Essentially, it is an array of arrays of numbers. All of this then representing all of the characters and the utterance that we had. Now, there are some language-specific and genre-specific issues. For instance, language modeling for morphologically rich languages. How are we going to select the subword units? Just modeling with morphological categories. Now, we also have to handle languages that don't have word segmentation, something that we spoke about earlier. And then also handling spoken versus written languages. And also within that, sometimes the written language can be very different than the way that people verbalize the language itself. For instance, I know with me, where I will write very differently than I speak. And also, people, when we tend to speak, will use a lot of jargon, so words specific to whatever industry we may work in or any specific industry that we are referring to at the time. So that's also a challenge. So pronunciation model. Pronunciation model is used to select, define, and use the symbols to describe an acoustic realization for an utterance. And what that means is that it's a dictionary where each word is represented as a phone segment. And here also on this slide we have a picture of that. Now there's two types of pronunciation modeling. The first is explicit pronunciation modeling, and the second is implicit pronunciation modeling. So here's an example. The pronunciation model itself works at the phoneme level. So in this, the variants are realized by phoneme substitution, deletions, and insertions. Welcome to the multilingual speech demo. In this demo, we will understand how to write multiple languages to a single MP3 file. Now, go to the Start menu of your window and open a Jupyter Notebook. Once the Jupyter Notebook is initialized, you'll see the link redirecting to the browser. Now, click on New and then Python 3 to create a new Python project. Let's rename this file as multilingual speech. Now, let's see how to implement this task. First, let's import the required packages using the import command. Import GTTS from GTTS. Let's write hello in English to a file named hello.mp3. To do so, we will use the GTTS function where we pass the text hello and the language en as parameters. Then we'll use the save function to save the file as hello.mp3. Make sure that you specify the complete path to the file. Now, run the code, and you'll see that hello.mp3 file is created in the specified location, as shown on the screen. Now, let's write hello bonjour in English and then French to hello bonjour.mp3. Here you can define a language and write the same output to a single destination file. To do so, let us declare two variables, tts_en and TTS_FR that will write hello in English and bonjour in French. Let's now create a file as hello_bonjour.mp3 using the with open function, which will write the words, both English and French, to an audio file using the code. TTS_en dot write to FP with a parameter F. TTS_FR_write to FP, passing in parameter F. Now run the code. Oops, we have an error saying P is not defined. That error occurred because we created the audio file and saved it to the variable F and not P. So let's change P to F and run the code again. You can now see that hello_bonjour.mp3 has been created in the destination folder. Run the audio file and you can hear hello in English and bonjour in French. Here we have successfully completed the execution of multilingual speech by writing multiple languages to a single MP3 file. So key takeaways from this module have been understanding multilingual speech, issues that arise when handling multilingual speech, and then different language speech synthesis techniques. Thank you. Module 6, Speech Translation. After completing this lesson, you should be able to understand speech translation, introduction and architecture, speech-to-speech translation, the speech processing interactive creation and evaluation, or SPICE toolkit, and working with speech-to-speech translation. Part 1, Speech Translation, Introduction and Architecture. Speech translation is the automatic conversion of text and speech from one natural language to another. So here as an example, we see on the left the phrase, "Be the change you want in the world," translated into another language. Why do we need machine translation? Well, taking India as an example, there are 4 different language families, 22 scheduled languages. There are 11 languages with more than 25 million speakers, and 30 languages with more than 1 million speakers. And only India has 2 languages in the world's 10 most spoken languages. And 7 to 8 Indian languages are in the top 20 of the most spoken languages. So, as you can imagine, it's very hard to communicate to each and every Indian citizen. And also, communicating in multiple languages is messy. And this is where speech translation can help in communicating a message in one language to reach or rather distribute to multiple languages. Some examples of speech-to-speech translation systems are Amazon's voice translator and also the Google Voice Translator. So here we see a simple speech-to-speech translation architecture. So on one side, we have our input speech on the left-hand side rather. We run that through automatic speech recognition and generate a text. We then run that through machine translation, which outputs yet another text. We run that through text-to-speech synthesis, and then we output the language that we desire to have our text in. So in this first step, the automatic speech recognition, that's where we're going to be transcribing the source speech as text. And in machine translation, we translate that transcribed text into the target language. And then in text-to-speech synthesis, we generate the speech in the target language from the translated text. Part 2, speech-to-speech translation. So statistical machine translation, or SMT for short, is the use of statistical models that learn to translate text from a source language to a target language given a large corpus of examples. So another way to look at that is, given a sentence T in the target language, we seek the sentence S from which the translator produced T. We know that our chance of error is minimized by choosing that sentence S that is most probable given T. Thus, we wish to choose S so as to maximize PR of S and T. Another concept here is neural machine translation, or NMT. And all this is the use of neural network models to learn a statistical model for machine translation. Now, the key benefit to this approach is that a single system can be trained directly on source and target text. So it no longer requires a pipeline of specialized systems that's used in typical statistical machine learning. And unlike traditional phrase-based translation systems, which consist of many small subcomponents that are tuned separately, with neural machine translation, what it attempts to do is build and train a single large neural network that will read a sentence and output a correct translation. Welcome to the speech-to-speech translation demo. In this demo, we are going to see how to recognize the speech-to-text and translate it into another language as required. As a first step, go to the Start menu of your window and open the Jupyter Notebook. Once the Jupyter Notebook is initialized, you can see the link redirecting to the browser. Click on New and then Python 3 to create a new Python project. Let's rename this notebook to Speech-to-Speech Translation. Now, let's see how to implement this project. First, we need to import the required packages. Here, we will be using speech recognition for analyzing text from audio files, as shown on the screen. Now, we will capture the data from an audio file using the record function. To do so, first load the audio file using the audio file function and specify the path. Please remember to use the complete path of the file that's shown on the screen. Now, run the code cells in case you haven't done it yet. All of the magic in speech recognition happens with the Recognizer class. Creating a Recognizer instance is easy. In your current interpreter session, just type r equals sr.recognizer and run the code cell again. Use the record function to capture data from a file. Type the following into your interpreter session to process the contents of the WAV file, which is located in one of your system directories. With text underscore data as source, audio equals r.record source. The context manager opens the file and reads its contents, storing the data in an audio file instance called source. Then the record method records that data from the entire file into an audio data instance. You can confirm this by checking the type of audio using type and passing in the audio variable. Run the code cells and you can see the output is shown on the screen. Now, let's invoke the recognize underscore Google method to attempt to recognize any speech in the audio. Depending on your internet connection speed, you may have to wait several seconds before seeing the result. Run the code, and you'll see the output is shown on the screen. Let's now see how to translate any text from one language to another. To do so, you can use Google Translator. Start by importing Translator from Google Trans and using the translator function to then fetch the translated value and store it into the variable translator. Use the translator.translate function and pass the text and the target language as parameters. Run the code, and you can now see the output is shown on the screen. You can see that, in this example, we are translating the speech from English to Latin. You can see that the output of the speech word will be printed in Latin. Here, we have successfully completed the process of performing speech-to-speech translation. Part 3, the Speech Processing Interactive Creation and Evaluation, or SPICE Toolkit. So SPICE was created under a National Science Foundation grant back in 2004 and was a 3-year-long project. The principal investigators are Tanya Schultz and Alan Black. And what this was meant to do is bridge the gap between technology and language experts. And to be a complete toolkit for this, it entails automatic speech recognition, or ASR, machine translation, or MT, and also text-to-speech, TTS. A few of these we've seen before. And it's used to develop web-based intelligent systems, where you have what's called user-in-the-loop interactive learning. And with user-in-the-loop systems, what that means is that there's always a user involved in some part of the system. It is not fully autonomous. So SPICE aims, at the end of the day, to significantly reduce the amount of time and effort involved in building speech processing systems for new languages. And what it really does is it provides innovative methods and tools. It will evaluate results, allowing for iterative improvements, develop speech processing models, and also use for collecting appropriate speech and text data to build these models. So this is a toolkit for all of this, quite comprehensive. Now SPICE was standing on the shoulders of giants, and it leveraged mature projects, including GlobalPhone and FestVox. It also implements bootstrapping techniques, which are based on extensive knowledge and data sharing across languages, as well as sharing across system components. Examples for data sharing techniques include the training of multilingual acoustic models across languages based on the definition of global phone sets, so something that we've looked at previously. And And also it uses sharing across components, or rather the sharing across components happens on all levels between recognition and synthesis, including phone sets, pronunciation dictionaries, acoustic models, and text resources. And it leveraged mature projects, including Global Phone and FestVox. It also implements bootstrapping techniques, which are based on extensive knowledge and data sharing across languages, as well as sharing across system components. Examples for data sharing techniques include the training of multilingual acoustic models across languages based on the definition of global phone sets, so something that we've looked at previously. And also it uses sharing across components, or rather the sharing across components happens on all levels between recognition and synthesis, including phone sets, pronunciation dictionaries, acoustic models, and text resources. So here is an overview of a speech-to-text translation system. Ultimately on the left we have outputs, or inputs rather, and then we also have our outputs, going from our source language, outputting our target language. Part 4, working on speech-to-speech translation. So the first thing we are going to do is load the data. And the file that we're going to use here, well, there's two. We have a small vocab EN file which contains English sentences, and then their French translations are in another file called small vocab FR. And so here within 2 lines of code, we can load both our English sentence file and our French sentences. Now, each line in the small vocab EN file contains an English sentence with its respective translation in each line of small vocab French. In other words, line 1 in the English matches up to line 1 in the French. And we can see that if we just print out a few lines from each of the files, which is what this small piece of code does here. Now, the complexity of this problem, though, is determined by the complexity of the vocabulary itself. And as you can imagine, a more complex vocabulary is going to give a more complex problem. So here is some code that's going to help us look at the complexity of the data set that we are going to be working with. Now next, what we want to do is pre-process the text. So what we're going to do is convert the text into sequences of integers using 2 methods. We're going to tokenize the words into IDs, so we've seen tokenization before. And then we're going to add padding to make all of the sequences the same length. And then we're going to also tokenize. So we're going to turn each sentence into a sequence of word IDs using Keris's tokenizer function. Previously we used NLTK. This time we're going to use Keris's tokenizer function, and we're going to use it to tokenize both the English and French sentences. And then the tokenization is going to return our tokenized input and the tokenized class. So here is some code showing how we are going to actually perform the tokenizer. And here we're just hard coding in 3 different sentences. The quick brown fox jumps over the lazy dog. By Jove, my quick study of lexicography won a prize. And finally, this is a short sentence. So that takes up almost a bulk of the code. First, we're just going to tokenize all of that, and then we'll print it out, and then you can see the output of that. And here is the ultimate output of that code. So at the top, we can see the word frequency, something that we have seen before when we were looking at NLTK. And then finally, our print output here. So for each of the sequences, for instance, quick brown fox jumps over the lazy dog, we get 1, 2, 4, 5, 6, 7, 1, 8, 9. And that same thing happens for sequence 2 and sequence 3. So now we've gone from words into numbers, which, as we saw before, computers like numbers, they do not like words. So next we have to take that and pad. And what we mean by that is we need to make sure that all the English sequences have the same length, and also all the French sequences have the same length. And we're going to do this by using Keris's pad sequences function. And here's some code that shows how we can do just that. Basically what it does is it checks the length of the max length, mind you, of each of these tokens, and then it will return a padded sequence if that needs to be done. And so ultimately we're going to get a padded tokenized output. And here is our padded list of sequences. And now each of these is exactly the same length, which is what we need for neural machine translation. Now this slide shows the code for our pre-processing pipeline. Now we're going to use Keras' sparse categorical cross-entropy function, as well as a few other wonderful things that it provides. Ultimately, what we're going to see here is the maximum English sentence length, the maximum French sentence length, and then the size of the English vocabulary and the size of our French vocabulary. Again, we're trying to get a sense of how complex our problem in this instance might be. So here is the output. We can see that our data was pre-processed and that our max English sentence length was 15, whereas our max French sentence length was 21. Our English vocabulary has 199 words in it, whereas our French vocabulary has 344. Not bad. Here we see an example of training a recurrent neural network rather, and the English words at the bottom and their French translations on top. Now, how exactly do we train this RNN or recurrent neural network? Well, we can do it with this code here. We have a number of inputs to our custom function that we've had, including input shape, the output sequence length, our English vocab size, and French vocab size, which is why we did all of that in the first place. And then we're going to use within this our GRU, the time distributed model, and a number of other things that we have pulled from the Keras libraries previously. And then ultimately what we're going to do is create a simple RNN model. We're going to fit our data to that using our pre-processed data, and then we are going to call the predict function to actually output the result. And here is the ultimate output of our model. We can see that it was trained on 110,288 samples and then validated on 27,573 samples. We have 10 epochs. We can see our loss function as we go in our value loss, and then ultimately the output of our sentence. And now the accuracy, we can also see, that's what ACC stands for, and we can see that our accuracy did increase over epochs. Now, epochs do take time. Here we did only 10 epochs, and it is possible that with more epochs, our model could actually become more accurate. Here it ended at around 60% accuracy. If you ran it for 40, 50, maybe even 100 epochs, if you can handle that amount of time, then our accuracy may actually be improved. That's something for you to test out on your own and see if it happens. See how it reacts to having more epochs. And then finally, we need the IDs to come back to text, right? So we need the neural network, which is translating the input words to IDs, but that isn't the final form we want. So for instance, when we looked at the output of the model previously, we have just a bunch of words seemingly strung together, but it's not necessarily a specific translation. While each of the words, yes, is translated, it's not really in the final form we want, a sentence that we could read. And so next, we're going to create a functions logits to text, which will bridge that gap for us between the logits from the neural network to the French translation. And that's what this code does here. So key takeaways from this section were speech translation. We provide an introduction, and then you saw an architecture. We discussed speech-to-speech translation. We discussed the speech processing interactive creation and evaluation toolkit, which you can use for this. And then finally, we saw an example of speech-to-speech translation using Keras. Thank you. Module 7, Spoken Dialogue Systems. After completing this lesson, you should be able to understand spoken dialogue systems, introduction and architecture, components of a dialogue system, voice XML and SSML, Olympus, and then deployment. Part 1, Spoken Dialogue System. A dialogue system is a computer program that communicates with a human user in a natural way. Here we have an example where we have our user on the left that interacts with the dialogue system via a CUI, GUI, or VUI. And on the other side of that is our computer-based application. Now there are a number of use cases here. We have different voice systems that you could interact with, spoken dialogue systems. We have use cases that work in cars, virtual assistants, tablet-based assistants, all sorts of different use cases for dialogue systems. Anytime where a user would want to have some type of interaction with a computer that can use voice. We'll look at 3 types briefly. The first is a text-based dialogue system, which is where a human can chat with the system itself. You'll see this on a lot of banking websites where you can get quick answers to questions just by merely chatting with the system. In the middle here, we see a spoken dialogue system where a human can interact on a turn-by-turn basis. In other words, kind of a back and forth. A lot of the phone trees that you may interact with where it says, please press 1 to do X or number 2 to do Y, and it goes back and forth with you like that. That is an example of one of these. And then finally, we have a multimodal dialogue system where it'll process 2 or more combined user input modes. However, within all of these, a spoken natural language interface plays a very important role in the spoken dialogue system communication. Now, here's an example of an architecture. And while different dialogue systems have different architectures, ultimately, they all have the same phases that they need to go through. So we start with input recognition, followed by natural language understanding, which flows into dialogue management, which then goes into response generation, and then finally, the output renderer is triggered. And that is the basic architecture of every dialogue system out there. These are all the steps that occur within them. So spoken dialogue systems have really been the most prominent component in today's virtual personal assistants, and you may have interacted with one or more of these. Examples are Microsoft's Cortana, Apple's Siri, Amazon Alexa, Google Assistant, and Facebook's M. And these, to a greater or lesser degree, allow you to go back and forth, or rather have a back and forth conversation with them. But currently, a lot of these systems are pretty limited in the amount of back and forth that they can have. However, they can chain together multiple commands in order to achieve some action. Now, here's an example of a spoken dialogue system architecture. It starts with text input. And in this example, we're running a hypothesis of, are there any new action movies to see this weekend? So we have a user that is trying to find this out. And their text input begins with, well, it begins with really their speech. So they're literally saying into the system, are there any new action movies to see this weekend? So that speech gets converted to text, which is then run through a speech recognition algorithm that feeds into a natural language understanding engine, or LU, for domain identification, user intent detection. User intent is, what does this user want to do? And then slot filling. So an example output of that might be a semantic frame, which is request movie. So the system has determined that that is what this user wants to do. They want to request a movie. And the genre of movie that they're looking for is action, and date is this weekend. So they want to request a movie, an action movie, and they want to see it this weekend. So that then gets fed into a dialogue management, or the dialogue management portion of the application, where you have dialogue state tracking, or DST, and dialogue policy. Now, the dialogue management may interact with one or more backend or knowledge providers, and these could be built in-house, or they could be third-party services that you're using and integrating with your system. Finally, from dialogue management, we flow into natural language generation, which is where the system itself actually determines the action that it should take and generates natural language in relation to that step. Here, we see that the system action or policy has decided that it needs to request the location from the user. So it generates a natural language response of where are you located and then sends that to the user. And so that is an end-to-end spoken dialogue system architecture. Now there's a number of libraries involved in these systems, 3 of which are here. We have a slot filling task library, database search library, and also an explanation task library. Now each of these libraries are written for an abstract task by referring to the task-oriented dialogue corpus. Part 2, components of a dialogue system. Here we can see the basic components of every dialogue system. It starts on the top left with an input decoder, which goes into a language understanding portion, which then goes into a dialogue manager, which interacts with domain-specific components. So as an example, a domain-specific component might be exactly what we saw in the previous example of movies. From the dialogue manager, we have our response generator, and then we have our output renderer. So let's look at the input decoder. Well, what the input decoder does is it recognizes the input and it converts that input into simple text. So here on the bottom right, we can see we have a speaker using voice that then gets fed into our automatic speech recognition or speech to text or STS, which is in of itself the input decoder, and from that we get our text. Now, keep in mind that besides speech, a dialogue system can have other inputs like gestures or handwriting or other things of that nature. So they aren't just limited to speech. Now, looking a bit deeper into the input decoder, it starts off doing a conversion of the spoken sound or user utterances to text, which is effectively just a string of words. Now, this requires the knowledge of phonetics and phonology. And phonetics is the branch of linguistics which deals with the sound of speech and their production, combination, description, and representation by written symbols. Phonology is the study of speech sounds in language or a language with reference to their distribution and patterning into tacit rules governing pronunciation. Now, for this purpose, speech recognition is needed. And systems for speech recognition are called automatic speech recognition, or ASR, computer speech recognition, or simply speech to text. The next part is the natural language understanding engine. So what does language understanding mean? Well, at the end of the day, what we're trying to do is understand what the user is trying to tell us. So the computer, rather, is trying to determine what the user is trying to tell it. And to do that, it converts the sequence of words into a semantic representation that can be used by the dialogue manager. So here on the left in our diagram, we see we have an NLP layer. NLP, again, stands for Natural Language Processing. So that's interacting with a knowledge base, which contains source content, and also with data storage, which is an interaction history, as well as analytics. And all 3 of these systems are interacting with each other in order to gain a natural language understanding. Now, looking at the input decoder, an input decoder involves the use of morphology, syntax, and semantics. Morphology is the study of structure and content of word forms. Additionally, after identifying the keywords and forming a meaning, it provides that to the dialogue manager. Now, the dialogue manager manages all aspects of the dialogue. First, it takes a semantic representation of the user's text. It figures out how that text fits into the overall context, and then it creates a semantic representation of the system response. So the dialogue manager does a number of things. It maintains the history of dialogue. It adopts certain dialogue strategies. It deals with malformed and unrecognized text, which is going to happen in pretty much every system that you'll build. It retrieves content stored in files or databases. It decides the best response for the user. It manages the initiative and system response. It handles the issue of pragmatics. It analyzes any discourse, and it also performs grounding. So as you can see, the dialog manager is a critical component of the system. It does a heck of a lot of things. So looking at the domain-specific components of our architecture, what is that? Well, a domain-specific component handles interfacing between the dialog system and external software. In other words, the database or export system or whatever else we have. And it'll convert queries and plans from the internal representation used by the dialog manager to the format used by the external domain-specific system. As an example of this, we have SQL. So in other words, it can take what came out of the dialog manager and convert that to SQL in order to interact with, say, a relational database system. Now, this can be handled by natural language querying processing systems, and it can also, as we said, generate SQL from natural language. But it really depends on what the system itself needs to do, and the systems, the subsystems, if you will, that it's going to interact with. But SQL is absolutely one example. Let's look at the output renderer. Well, in a dialog system, the output is rendered using the output renderer, as you may have guessed from the name. And it has two components. The first component is a text-to-speech engine, which is used to convert normal textual data into speech. And then secondly, it has what's called a talking head, which is used to encapsulate methods and techniques for generating and animating images or models of a character face. Now we have the response generator, which constructs the message that is to be given to the user. And this takes decisions regarding what information should be included, how information should be structured, the choice of words, and also the syntactic structure for the message. Now, current systems use very simple methods such as insertion of retrieved data into predefined slots in a template. In other words, it's almost like fill in the blank, where the system determines, okay, what words should we use, and then fits them into those templates, and then we get our output. Part 2, components of a dialogue system. Now, speech generation translates the message constructed by the response generation component into spoken form. And it could use pre-recorded canned speech, something like, welcome, how can I help you? Things that can be quickly retrieved from a database system and then just returned to the user. Or it could use text-to-speech synthesis, which is speech that is generated from text. So in other words, we can give them pre-created audio, or we can generate that audio response on the fly. So here's an example of speech generation. We have text coming in one side. We then perform some text analysis to get the utterance composed of words. We then perform a linguistic analysis, including phasing, intonation, and duration. We then have utterances composed of phonemes, from which we rather generate the waveforms, because as we saw in previous modules, all spoken speech is effectively waveforms. And then the output of all of that is speech. It's what you might hear Siri or Google Home or an Alexa ultimately saying to you. Dialogue systems are classified based on the method used to control the dialogue. Currently, there are 3 categories. On the left, we see there are frame-based systems. In the middle, we have a finite state or graph-based systems. And then finally, on the right, we have agent-based systems. In a finite state or a graph-based system, the user is taken through a dialogue consisting of a sequence of predetermined steps or stages. And the flow of the dialogue is specified as a set of dialogue states. Every phone tree that you've interacted with works in this manner. In a frame-based system, it first starts with using a template that it fills in from the user responses. The user is asked questions that enable the system to fill slots in a template in order for it to perform tasks. Whereas with a finite state-based system, where you are taking the user through a predefined set of steps, here the flow of dialogue is not predetermined and can go in multiple directions. But the flow of the dialogue ultimately depends on the content of user input and the information the user has to elicit. Finally, in agent-based systems, they allow for the complex communication between the system, the user, and the application. in order to solve some problem or task. Here, the interaction is viewed as interaction between two agents. Each of the interactions is capable of reasoning about its own actions and beliefs. And the dialogue takes the preceding context into account. So this is much like when, or if you and I were having a conversation where each sentence in our conversation, the back and forth that we're having, does take into account the preceding context. And finally, the dialogue evolves dynamically as a sequence of related steps that build on top of each other. Now, there are a number of challenges in building a dialogue system. First, you have to design the system prompts, which can be a very difficult task depending on the language that you're using and what it is you want your system to do. Then we have the challenge of grounding. There's detection of conflicts, plan recognition, problems relating to the utterance of the user, things like their accent and whatnot. And then finally, the computer's just general lack of understanding of natural language. As you might imagine, computers don't right off the bat understand natural language like you or I do. We really have to do a lot of work to get them to understand it. And that's where NLP and things of that nature come into play. But how do we evaluate a dialogue system? Well, there are metrics. And with these metrics, we're going to be evaluating the correctness of the total solution. As an example, we look at the percentage of slots that were filled with the correct values. We also look at measuring the system's efficiency at helping users, things like checking the total elapsed time for the dialogue. In other words, how quickly can the system get the user to where they want to be, or to help them do what they want to do. And we can also measure the user's perception of the system. Things like the number of times the ASR system failed to return any sentence or it rejected prompts. Things that might cause it to say, "I'm sorry, I didn't understand that." I've heard stuff like that from my Alexa a number of times. We can also measure the number of times the user had to barge in other words, interrupt the system, because it basically just started doing something that wasn't requested of it. Also, we can run a survey. We can ask the performance of the ASR or just ask the users about the performance of the TTS. And we can also get ratings. So look at the ease of the tasks, how good is the system response, all on a 1 to 3 or 1 to 5 basis, the interaction speed, user expertise, and system behavior. So these are all different ways that we might evaluate a dialogue system or have a user evaluate a dialogue system based on a star rating or how do they feel it did 1 to 10, whatever you want to use. Part 3, Voice XML and SSML. So Voice XML was designed for creating dialogues. Its major goal is to bring the advantages of web-based development and content delivery to interactive voice response applications. XML is a standard that has been around for quite a long time, and essentially Voice XML is just a version of that. Things that we can use Voice XML for instance, in creating an audio dialogue feature are synthesized speech, digitized audio, recognition of spoken and DTMF key input, recording of spoken input, telephony, and mixed initiative conversations. With Voice XML, there's 2 types of dialogues. We have forms and menus. Forms present information and gather input, things that we're all used to filling out. And then menus offer choices of what to do next. Here's an example of Voice XML. So if you're familiar with these XML standard, this will look very familiar to you. At the very top, we define our XML tag, and then we start defining our Voice XML, which starts with VXML. Pretty intuitive. And the VXML tag is our initial container for dialogues. And within this dialogue, we see that we have a form dialogue, which contains a block that synthesizes and presents hello world to the user. Here's an example of an architectural model that uses Voice XML. So on the bottom, we have our implementation platform. Now that then interacts with our voice XML interpreter context, specifically the voice XML interpreter. So what it does is then send a request to a document server, which returns the document through the interpreter and back out through the implementation platform. Now let's look at SSML. SSML stands for Speech Synthesis Markup Language. It's a lot faster to just say SSML. And what this does is it provides users with a standardized method for controlling different aspects of speech synthesis output. For example, with SSML, one can alter prosody attributes. For instance, the rate, pitch, volume. You can insert pauses of any length. You can change the speaking voice while reading. And there are also many other aspects of how the text is read by the synthetic voice, which is ultimately what this is helping to do. An example of this might be Google Maps. If you've ever used that, there are many different voices for Google Maps that you can change to use. And you can also change sometimes the rate, pitch, and volume of these voices. And that's what SSML helps with. So here's an example of what that looks like. Pretty close to our XML tags that we saw before. So you can see it starts with the open tag says speak. It's going to literally say hello readers. And then we can see that there is information about the voice itself. So here the name of the voice is David. It's a male, about age 25. And David is going to say, good day, is it tea time? Or David can also say, hey there, want some pie? So what this is doing is defining the voice itself, gender, name, age, and what that voice says in the context of this hello readers. So basically this is defining kind of a hello, a welcome, if you will. Part 4, Olympus. Olympus is a complete framework for implementing spoken dialogue systems. It provides a complete system to implement and test conversational agents. It incorporates the Ravenclaw Dialogue Manager, and it uses a Galaxy message passing layer to integrate its components. Now, Olympus supports multimodal interaction, mixed initiative interaction, and it also has components that handle speech recognition, understanding, generation, and synthesis. So in other words, it does pretty much everything that we need it to do. Here is what the Olympus architecture looks like. We start off with speech input, which gets fed into a speech recognition engine. As an example, that speech recognition might output 2 p.m., which then gets fed into a language understanding module where we see that time equals 2 p.m. That then gets fed into the dialogue management, where it's determined that the system needs to request the end time. So now because it needs to request something, it gets fed into the language generation module, which generates a sentence, until what time would you like the room? And then finally, that gets fed to the speech synthesis engine, which then literally says to the user, until what time would you like the room? So that's the architecture. As you can see here, it has every part of the system that we need. Part 5, deployment. Now, the deployment of systems for human-to-machine communication by voice requires overcoming a variety of obstacles that can affect the speech processing technologies. Things like variation in speaking style, acoustic noise, ambiguity of language, and possible confusion on the part of the speaker. Now, the diversity of these practical problems encountered in the real world leads to a perceived gap between laboratory and real-world performance. So if you have ever deployed a software system into production, then you know what that means, where you might run a test in a controlled environment and everything in your system works wonderfully, but then when it goes into production, it does not. Maybe you're testing with perfect data, which you do not have in the real world, or in this example with voice systems, in a laboratory, you have little to no other noise. But in the real world, a person could be walking down the street speaking into their phone. So lab conditions don't necessarily reflect real world conditions. And so when you're testing these systems, you want to test within as close to real world conditions as possible. Otherwise, you will, or users rather, will encounter a gap. So looking deeper at deployment, a simple voice communication with machines is now deployed in personal computers. You have automation of long distance calls and things like voice dialing on mobile phones. Now, these systems have small vocabularies and strictly circumscribed task domains. In other words, they are very task specific and they can't really do anything outside of the limited functionality that they were designed to provide. However, in research laboratories, there are much more advanced human-machine dialogue systems, where these systems have vocabularies of thousands of words, and they have the intelligence to carry on a conversation on specific topics. So there's truly some state-of-the-art systems, or are some really state-of-the-art systems out there, but currently they're limited to research laboratories, inside corporations. They're not deployed as much on, say, a mobile phone. Now, human-machine dialogue systems can be represented as a four-step process, as shown on this slide. It starts with speech. That speech gets fed into a speech recognizer, which converts the spoken input into text. That text then goes into a language analyzer, which extracts meaning from text. That meaning is fed into a computer, where it queries a database and constructs a reply in text format. And then that text reply again is fed through a speech synthesizer, which synthesizes the voice response and outputs speech. For the speech recognizer portion, you have speech models. The language analyzer is composed of grammar and semantics. The computer portion deals with an information database, and the speech synthesizer interacts with pronunciation rules. And all of these things need to be deployed together to have a complete system. Welcome to the Personal Voice Assistant in Python demo. In this demo, we'll see how to write a script for a personal voice assistant using Python. As we know, Python is a suitable language for scriptwriters and developers. The query for the assistant can be manipulated as per your needs. As a first step, go to the Start menu of your window and open the Jupyter Notebook. Once the Jupyter Notebook is initialized, you can see the link redirecting to the browser. Click on New and then Python 3 to create a new Python 3 project. Let's rename this notebook to Personal Voice Assistant. Now, let's see how to implement this project. Let's first import all the speech recognition packages from the Google API and the other dependent packages. As shown on the screen, we're importing speech recognition as SR, importing play sound, which is used to save the MP3 file, importing GTTS, or rather GTTS from GTTS, which is used to convert the text to speech, then importing OS, which is used to open or save a file, and importing Wolfram Alpha to calculate strings into formulas, and also importing WebDriver from Selenium to convert browser operations. Now, we'll create two functions, getAudio, which will take audio as input and process it to provide the required response, and another, assistant_speaks, which is static responses for each of the speakings. We're going to trigger both of these functions from the main function. In this case, let's first write the code, which will save the text to the audio files. To do so, let's define the function assistant_speaks and declare a global variable num, which will be used to rename every audio file with different names to remove ambiguity. So every time the output comes in, the value of num will increase by 1. We then use the gtts function, which takes a parameter as text, which is to be converted, the language to be converted in, and the duration. Once the text is converted, we must save it in an audio file. So we specify the file in the specified location. Do remember to specify the complete path of your local disk and save the file with an extension of .mp3. Now, we'll use the playSound package that we've imported in the beginning of the code. The playSound package is used to play a file. So, using the code below, playsound.playsound, passing in file and true, and then os.remove, passing in the file to remove. We have seen that the assistant speak function takes output as a parameter. Let's write the code to calculate the output. That is, let's define the function getAudio that will take the audio file and return it as the function output. As you can see the code on the screen. Let's now examine this code. Here, we use the sr.recognizer function, which recognizes the audio and stores it into an object. We then use the sr.microphone function, which is used to enable the microphone. And we print a message speak, which indicates that the audio can be recorded. Now, we need to record the audio using the speech recognition library, for which we use the listen function, which will read the audio and take the source and time limit as parameters. That means it'll read the input for a limit of 5 seconds. Now, we use the recognizer.google function in the try block, which will take the audio as an input and recognize the text in the voice. It will print whatever is spoken in the audio and return it in the form of text. If there is any exception, anything happens that we don't expect, it will print could not understand the audio, please try again. Now, run all the code cells. Since we have declared both the functions, let's declare the main function and all the functions for execution. Where we will write the code called the driver code, which is where we'll call the assistant speaks function and pass the text, "What's your name, human?" as a parameter. And then we'll get call the getAudio function, whose output is stored in the variable name. Then we declare a while loop, where if the condition is true, the assistant speaks, "What can I do for you?" And based on the input, it will continue or say, "Okay, bye," followed by your name. And lastly, we call the process text function, which is used to process the query. Run the code, and you'll see the output as shown on the screen. Oops, we have an error. Let's check the code again. Everything looks good. Just run all the code cells again in case we have missed doing something before. And now you can see the output. It says, "What's your name, human?" You can speak for 5 seconds and then stop. It reads Narendra. Again, it asks, "What can I do for you?" And again, you can give input or speak for 5 seconds. So here we've got an idea how we're giving voice to the machine and taking an input from a user. Here, we have successfully completed the implementation of a personal voice assistant in Python. So, now that you've gone through this module, you have an understanding of the architecture of spoken dialogue systems, the various components of dialogue systems. We've looked at voice XML and SSML. We looked at Olympus and how it provides really everything that we need for us to build one of these systems on our own. And then finally, we looked at deployment. Thank you. Module 8, Voice Conversion. After completing this lesson, you should be able to understand how voice conversation works, identification of similar voice, and de-identification of voice. Part 1, Introduction to Voice Conversion. Voice conversion is a technique to modify speech waveform to convert non- or paralinguistic information while preserving linguistic information. So as an example, we have our input, and then we perform voice conversion. And that can be converted as if uttered by a specific target speaker, uttered by a specific target speaking style, or uttered by a specific linguistic content. And then finally, we have our output. So some terminology around this is voice transformation, voice conversion, voice morphing, accent conversion, and cross-language conversion. But why is this even needed? Well, it's possible to break down the barriers from the speech communication. So as an example, we have our speech input, which then goes through excitation generation, articulation, and then finally voice conversion. Now, it's possible to augment our speech production by intentionally controlling non-linguistic information. So for instance, we can do excitation generation, which is beyond constraints, articulation beyond constraints, and then produce converted speech. So there are a number of applications of voice conversions. For instance, customization of text-to-speech systems, voice editing and dubbing, personalized human-computer interfaces, there's medical applications, and there's also a host of other applications as well. So how do we actually convert speech? Well, it's a pipeline, much like we've seen with everything else. We have our input, we perform an analysis, we then convert that speech, we synthesize it, and then output is converted speech. Now within this, we have what are called speech parameters, which are extracted from the speech signal. So examples of these are the pulse train, Gaussian noise, and excitation. These get run through the synthesis filter, which is here labeled as a spectral parameter, and then output is synthetic speech. Part 2, automatic speaker recognition. Speaker recognition is the process of recognizing the speaker with the help of speaker-specific information that's included in the speech sounds. Now this involves speaker identity, which is the physiological and behavioral characteristics of the speech production model of an individual speaker. That's really what speaker identity is. Now there's a number of applications of automatic speaker recognition. For instance, banking over a telephone network, telephone shopping and database access services, voice dialing and email, information and reservation services, security control for confidential information, and also forensics and surveillance applications. Probably one of the more common ones that you may have dealt with is banking over a telephone network or telephone-based shopping. Speaker identification is the process in which the speaker providing the input speech is determined. And here's an example of how that might work. On the left-hand side, we have the input provided by the speaker. We then perform feature extraction, and then we look for similarities using one or more reference templates. And we could run one or more similarity measures using all of these different templates. From there, we pick our maximum. So in other words, which one of these is the closest to the person doing the speaking, and from that, we then get a speaker ID. Part 3, phonetic SID system. A phonetic SID system is a system used to apply a statistical model of a speaker's pronunciation. Now the model here is trained on the phone sequences which are derived from the speaker's utterances. In other words, we're training the model on the dialogue from the speaker. Now the recognition is performed with something called a Viterbi search, which uses a fully connected null grammar network of monophones. And here's what this might look like. We have our input on the left, which then gets fed into a phonetic recognizer, which is then fed into an LSPM scoring module, which means language dependent speaker phonetic model, or rather it uses one. And then we have some decision logic that's applied based on what the model provides. Part 4, speaker de-identification. So speaker de-identification systems conceal the speaker's identity from their spoken utterances while still preserving the intelligibility of the pure depersonalized linguistic information. You may have seen these actually being used on TV programs where they're trying to conceal the identity of someone doing the speaking, where they don't want you to be able to tell who is doing the speaking, but they do want you to be able to understand what that person is saying. So herein, voice characteristics of the speaker have to be identified by the system and then modified by different voice features without losing any of the information. An efficient speaker de-identification system has to be capable of accomplishing 3 main tasks. First, the system has to hide the speaker's true identities from their spoken utterances. Second, the system has to preserve voice quality of the de-identified speech. And third, the system has to allow authorized listeners to retrieve the original identity of the source speaker and avoid unauthorized listeners to re-identify the source speaker. Because if you could identify the source speaker, that would get around the entire goal of de-identification in the first place. So below are some of the applications of speaker de-identification. So as mentioned previously, this could be applied to protect witnesses in investigations, whistleblowers, and journalist sources. It can be used to preserve the privacy of individuals against their confidential medical information. So if someone wanted to provide confidential medical information but did not want anyone to be able to trace it back to them specifically, that would be an example here. And then third, it can also be exploited to assure the freedom of expression and democracy in public domains. So perhaps in countries where freedom of speech is not allowed or freedom of speech is suppressed, people could still feel free to express their thoughts and feelings, but through the process of de-identification, you would not be able to identify who specifically said those things. Now, one technique that is used here is called frequency warping, VTLN, speaker de-identification. First, the speech signal is segmented synchronously with the pitch periods of the vocal tract. Next, each segment is filtered by the Hamming window function. After that, a forward discrete Fourier transformation is performed, and we've seen Fourier transformation used previously. After that, using specific warping functions and the associated warping factor, the frequency axis of the segments is warped. After that, a backward discrete Fourier transformation is performed. And then finally, segments are changed using PSOLA, or pitch synchronous overlap and add method. So here's an example of the difference between the original signal and the de-identified signal. While both of these visualizations look fairly similar, they're dissimilar enough to not be able to identify the source of the utterances. And so you can see that there is definitely a bit more green and a bit more blue on the bottom visualization. Welcome to the speaker identification demo. In this demo, we'll use a real-world dataset and build a speech-to-text model to identify the voice of speakers. As a first step, go to the Start menu of your window and open the Jupyter Notebook. Once the Jupyter Notebook is initialized, you can see the link redirecting to the browser. Click on New and then Python 3 to create a new Python project. Let's rename the file as Speaker Voice Identification. Now, let's see how to implement this project. Let's first begin by importing all the required packages using the import command. First, we import OS and Librosa, then import ipython.display as PLT, import numpy as NP, and import wavefile from scipy.io. And finally, import warnings, which will use the filter warnings function to ignore the warnings. Now, let's extract the labels of the training dataset. To do so, define the path of the audio file. Remember to give the complete path from the local disk as shown on the screen. Then we will use the os.listdir or list directory function, which will extract the labels from the audio and store them in the variable labels. Now, let's read the audio waves and use the below pre-processing steps to deal with this. Here's the 2 steps we'll follow. Step 1, resampling. Step 2, removing shorter commands of less than 1 second. As you can see, we resample the label extracted from the audio that ends with .wav. Let's perform data pre-processing on the audio file. Here, we declare 2 arrays as all wave and all labels, and we extract the labels with the .wav extension. Then, we use the resample function, where we resample the labels based on the samples and the sampling rate. Now run the code. Oops, we have an error. Let's examine the error. We have redefined the training audio path. Let's remove it from here and rerun all the code cells in case we have missed doing it before. Now, let's convert the output labels to integer encoding. To do so, we import label encoder from sklearn.preprocessing. To perform the encoding, we call the label encoder function and transform all the labels using the le_fit_transform function. Now, convert the integer encoded labels to a one-hot vector, since this is a multi-classification problem. To do so, we import np_utils from keras.utils. And to convert the encoded vectors, we'll use the nputils.to_categorical function. Now, let's reshape the 2D array to 3D, since the input to the convolutional 1D must be a 3D array. This can be done using the reshape function as shown on the screen. Now, splitting into training and validation sets. Next, we will train the model on 80% of the data, in other words, the training data set, and validate on the remaining 20%, which is our test set. To do so, we import train test split from the sklearn model selection, and then use the train test split function as shown on the screen. Run all of the code cells. Now, the major step in this process is building or implementing the model using the Keras functional API. You can see the code on the screen. Let's take a quick look. So what we're going to do is import dense, dropout, flatten, conv1d, input, and max pooling 1d from keras.layers. Then we import model from keras.models, import early stopping and model checkpoint from keras callbacks, and finally import backend as k from keras. Then we use the input function to define the shape. Now we have defined the first, second, third, and fourth conv1d layers using the conv1d function, max pooling 1d function, and the dropout function. We then use the flatten function to define the flattened layer. Similarly, we use the dense function to declare the dense layers 1 and 2. Once the dense layers are defined, the output of the dense function is stored in the outputs variable, which is based on the labels and the activation value. And then the inputs and the outputs are passed as parameters to the model function to create a model. Now run all of the code cells in case we missed doing it earlier. Now let's calculate the cross entropy. To do so, we use the mode.compile method, which takes the loss value, optimizer value, and the metrics as parameters. We define the early stopping and model checkpoints using their respective functions. Early stopping and model checkpoints are the callbacks to stop training the neural network at the right time and to save the best model for every epoch. Finally, the functions require verbose value as a parameter, based on which the callbacks are performed. Now, let's write the code for model fitting, where we use the model.fit function, which calculates the history based on the epochs or epochs, callbacks, batch size, and the validation data. Run the code, and you can see the output that shows the training samples, validated samples, and epoch value. This may take some time to run. Meanwhile, we can plot the accuracy graph and examine the performance. Let's examine the code for doing this. As you can see on the screen, we're importing pyplot from matplotlib. We can now use the plot functions to plot the graph based on the labels to train and test the model. And we use the show function to display the accuracy graph so plotted. The process ends here. Since the model building may take a lot of time, possibly more than 3 to 4 hours, depending on your CPU utilization. Hence, we successfully completed the process of speaker identification, where we use a real-world dataset and build the speech-to-text model to identify the voice of speakers. So, now you have an understanding about how voice conversion works, the identification of a similar voice, how a system might do that, and then also how de-identification of voice is performed. Thank you.